Hello there and welcome to Life Beyond Seen, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're heading somewhere very few humans have ever truly visited. Not the top of a mountain, not the far side of the moon, but the deepest place on our own planet. The Mariana Trench. A stretch of ocean so deep and so dark that it still feels like a secret Earth is keeping from us. And the question we're exploring is a deliciously unsettling one. What prehistoric creatures might still be hiding down there? Not in the sense of a movie monster with glowing eyes and dramatic music behind it, but in the quiet, scientific, surprisingly plausible way. The kind of creature that doesn't need to roar to be terrifying. The kind that simply survives, unnoticed, in a place where almost nothing should. So let me ask you something gently before we begin. Where are you listening from tonight? And what time is it for you right now? Because while we talk about the deepest trench on Earth, we're all here together, spread across time zones, each of us drifting through our own little pocket of evening. And if you find this calming, intriguing, or simply the kind of story your brain enjoys while it powers down, I'd be grateful if you liked the video and maybe subscribed. It helps this little corner of quiet science reach more people who could use a peaceful place to land. Now, settle in, let your shoulders drop, let your thoughts slow down, because we're about to take a long, careful descent into a world that doesn't behave like the one we know. A world where pressure crushes, sunlight never arrives, and life still finds a way. And somewhere in that darkness, the ocean might still be holding on to creatures that feel like they belong to another age entirely. The Mariana Trench is not just deep. It is almost offensively deep. It is the kind of depth that makes your brain do that little stutter where it tries to picture the distance and fails halfway through. If you've ever looked at the ocean and thought it felt endless, the trench is what happens when the ocean decides it wasn't done yet. It lies in the western Pacific Ocean, east of the Philippines, near Guam, like a long curved scar in the Earth's crust. And within that trench is a place called Challenger Deep, which is the deepest known point in the ocean. If you could take Mount Everest and drop it into Challenger Deep, the peak would still be underwater. That detail alone is enough to make most people sit a little more still. But depth is only one part of the story. The real strangeness begins when you understand what that depth does to everything down there. The pressure is immense. It increases by about 1 atmosphere for every 10 meters you descend. At the bottom of Challenger Deep, you're dealing with more than 1,000 atmospheres of pressure. That's like having the weight of a small mountain pressing down on every square inch of you. If you tried to go down there without a specialized vessel, your body would not slowly struggle. It would not have a dramatic final moment. It would be crushed in an instant, like a soda can under the heel of a boot. It's not a friendly place. It's not a place humans were built to visit. And yet, life is there. That's the part that never stops being strange. Life exists in the trench, not as a rare accident, but as a functioning ecosystem. It's not just one lonely creature drifting through darkness. It's communities, it's food webs, it's predators and prey and things that glow and things that crawl and things that look like they were designed by someone who had never seen an animal before and was working purely from nightmares. So when we ask what prehistoric creatures might still hide there, we're not asking whether life can exist. We already know it can. The real question is, what kind of life can survive when everything about the environment is trying to make survival impossible? And that's where things get interesting. When people hear the phrase prehistoric creature, they often picture dinosaurs, a Tyrannosaurus, a Triceratops, a huge creature stomping through a fern-covered landscape, followed by dramatic music and a narrator whispering, "It was the age of giants." But the ocean's version of prehistoric is different. The ocean doesn't just preserve bones, it preserves body plans, it preserves strategies. It keeps ancient designs alive because the deep sea changes slowly, very slowly. On land, environments shift constantly. Ice ages come and go, forests turn into grasslands, rivers change course, continents collide. But the deep ocean is stable in a way the surface world isn't. Cold, dark, quiet. the same basic conditions for millions and millions of years. That kind of stability is perfect for ancient survivors. It's also perfect for things we haven't met yet, because the Mariana Trench is not a well-lit aquarium with labelled tanks. It's not a place we've mapped in detail with thousands of cameras. It's a place we've barely touched. The deepest parts of the ocean are still less explored than the surface of the moon. That isn't an exaggeration. It's a reminder that we live on a planet where a massive part of it remains unknown, and that unknown space is where imagination tends to run wild, sometimes too wild, sometimes in ways that ignore biology and physics entirely, but sometimes it wanders into ideas that aren't as far-fetched as they sound. For example, what if a creature we thought was extinct didn't actually disappear? What if it simply moved deeper? There's a certain comfort in the idea that extinction is final, that when a species vanishes, it's gone. We close the book. We put the fossil in a museum. We tell ourselves the story has ended. But the ocean is very good at hiding stories. There are animals alive today that feel like they should be fossils. The coelacanth is a famous example. It's a fish with lobed fins that looks like something you'd expect to see in a textbook about the Devonian period. For a long time, scientists thought it had gone extinct about 66 million years ago. Then one was caught off the coast of South Africa in 1938. Alive. Real. Not a rumour. That discovery was a warning. A polite one, but still a warning. It told us that the ocean can keep secrets for a very long time, and if the ocean can hide a fish for tens of millions of years, it can hide other things too. Now, to be clear, the coelacanth does not live in the Mariana Trench. It lives in deep waters, but not trench depth. Still, it's a symbol. It's proof that ancient lineages can persist in the shadows out of sight while humans assume they're gone. And that brings us to the trench itself. What kind of creatures do we actually know live down there? The answer is both fascinating and slightly disappointing depending on what you were hoping for. You won't find a plesiosaur gliding through the darkness. You won't find a mosasaur waiting like a submarine with teeth. But you will find animals that look alien enough to satisfy the part of your brain that loves deep-sea mysteries. One of the most common trench residents is the amphipod. Imagine a shrimp, but not the neat, clean shrimp you might picture from a seafood restaurant. This is a shrimp-like scavenger with a body designed for the deep. Some amphipods in the trench are large compared to their shallow water relatives. They have tough exoskeletons and a habit of showing up quickly when something dies and sinks. And that's one of the key realities of trench life. Food is rare. Nothing grows down there in the way it grows on land. There's no sunlight, no plants, no photosynthesis. So most of the food comes from above. Dead plankton, bits of organic debris, fecal pellets drifting down like a slow, grim snow. And occasionally something big. A fish, a whale, a large animal that dies and sinks, becoming a temporary feast. When something like that hits the bottom, it's like a dinner bell in the dark. Creatures arrive, they feed, they compete, they disappear again. This is not a place of constant abundance. It's a place of patience and opportunism, and that environment favours certain kinds of animals, the ones that can survive long periods with very little food, the ones that don't waste energy, the ones that can sense a meal from far away and reach it before it's gone. That's a prehistoric theme in itself. Many ancient creatures weren't fast and flashy. They were efficient, built for endurance, built for survival in harsh conditions. In the trench, those traits are still valuable. Another group of animals found in trench environments are sea cucumbers, specifically a type called holothurians. Some of them are almost delicate looking with translucent bodies and soft shapes. But don't let that fool you. They are tough in their own way. They crawl along the seafloor, consuming sediment, extracting nutrients, and leaving behind processed material. It's not glamorous, it's not dramatic, but it's life, and it's part of the system that keeps the trench from being a dead zone. There are also polychaete worms, which are bristly segmented worms that can thrive in deep environments. Some of them burrow, some of them crawl, some of them hunt. Their bodies are simple but effective, and that's another theme you'll see over and over again in deep-sea life. Simple shapes, efficient designs, things that don't need to be pretty, they just need to work. But what about fish? Yes, fish live deep too, and one of the most famous deep-sea fish associated with trenches is the snailfish. Not the shallow water snailfish you might find near a coastline, but specialised trench snailfish that can withstand enormous pressure. These fish are not sleek and muscular like tuna. They are soft-bodied, gelatinous. Their bodies are adapted to pressure in a way that makes them look almost fragile. But that softness is part of their strength. In the deep, having rigid structures can be a disadvantage. Pressure can crush air spaces, it can distort hard tissues. So many deep-sea creatures have bodies that are flexible, with fewer cavities and less calcified structure. Even their proteins and cell membranes are adapted. At extreme depths, the chemistry of life itself has to change. Some deep-sea animals use molecules called pizzolites, which help stabilize proteins under high pressure. One example is trimethylamine N-oxide, often shortened to TMAO. It's one of those details that makes you realize the trench isn't just a place with weird animals. It's a place where the rules of biology are being pushed right to the edge. And when biology is pushed to the edge, it can create creatures that feel ancient, because they represent older, more basic solutions to survival. Now, when we talk about prehistoric creatures hiding in the trench, we should also talk about something else. The deep sea doesn't just preserve ancient designs, it also creates new ones that look ancient to us. Because when you remove sunlight, remove easy food, remove warmth, remove familiar landscapes, evolution has a different playground. The result is a world filled with animals that look like they belong to another planet, but they're right here on Earth, beneath us, doing their quiet work in the dark. There's a particular kind of fear that comes with deep water. Not the fear of drowning exactly, something older, something closer to instinct. It's the fear of not knowing what's beneath you. If you've ever swum in the ocean and suddenly realised you couldn't see the bottom, you might know the feeling. The water becomes a void. Your imagination fills it with shapes. The trench is that feeling turned into geography. It's a real void, and it's not empty. So could something large be down there? That's where we have to be careful. The trench is not a place where giant predators would easily thrive. Food is limited. The ecosystem doesn't support the kind of biomass needed for huge animals to live comfortably. Big bodies require big meals, and big meals are not guaranteed. But that doesn't mean large animals are impossible. It means they would need a strategy. They would need to be extremely efficient. They would need to move slowly. They would need to be able to go long stretches without eating. If you think that sounds like a shark, you're not wrong. There are deep-sea sharks that already fit some of those traits. The Greenland shark, for example, lives in cold, deep waters, and it has an incredibly slow metabolism. It can live for centuries. It moves slowly. It's not built for fast chases. It's built for persistence. It's not a trench creature, but it shows you what happens when an animal evolves for cold, deep, slow living. The sleeper sharks, a group that includes the Greenland shark, have an ancient feel to them. Their movements are heavy. Their eyes can look cloudy. Their bodies seem like they belong to a different era. And sharks themselves are ancient. They've been around for hundreds of millions of years, long before dinosaurs. So when people imagine prehistoric creatures in the deep, sharks are a reasonable starting point. But the trench is deeper than where most sharks live. Still, sharks don't need to be in the deepest part to be part of the trench story. The trench has slopes. It has regions that are deep but not the deepest. It has areas where a large predator could potentially roam. If a creature wanted to hide from humans, it wouldn't necessarily need to live at the very bottom. It would just need to live where humans rarely go. And humans rarely go anywhere below a few hundred meters. That means the deep ocean, in general, is already a hiding place. Now let's talk about another kind of prehistoric feeling. Not size, not teeth, but shape. Some deep-sea creatures look like they belong in a fossil record because their body plan is so old. Take the nautilus, for example. It's a living cephalopod with a spiral shell like a floating piece of ancient geometry. It's not a trench animal either, but it represents a lineage that goes back hundreds of millions of years. It's a reminder that the ocean doesn't always replace old designs. Sometimes it keeps them. Then there are animals like the frilled shark, which looks like something that swam out of a Cretaceous nightmare. It has a long body, strange jaws, and a habit of living deep. It's rare, but it exists, and it feels prehistoric because it is. But the Mariana Trench isn't just about known creatures. It's also about what we don't know. There are organisms down there that have never been seen alive by a human eye, not in person, not in a lab tank, not under a microscope after collection. Some deep-sea animals are so fragile that they fall apart when brought to the surface. Some are so rare that we've only captured them once. Some might exist in pockets we haven't sampled. And that's where the prehistoric creature idea becomes more interesting. Because if something down there is rare, elusive, and fragile, we might never find it with the methods we use. We tend to find what is easy to find. We find scavengers because they come to bait. We find things that can survive collection. We find animals that can handle the stress of being captured. But what about the ones that don't come to bait? What about the ones that avoid disturbance? What about the ones that are soft and break apart? What about the ones that live in narrow zones tucked into the trench walls? There's a whole category of life that could be underrepresented in our knowledge simply because it's hard to detect. Jellyfish and other gelatinous creatures are a good example. In shallow waters, jellyfish blooms can be obvious. In the deep sea, gelatinous life can be everywhere, but it leaves almost no trace. If a fish dies, it might leave bones. If a squid dies, it might leave beaks. If a jelly-like creature dies, it might simply dissolve into the water and vanish. So if the deep ocean holds creatures that are large but soft, they could be harder to prove. And that's not fantasy, that's biology. There are already large gelatinous animals in the ocean. Some siphonophores, which are colonial organisms that function like a single creature, can be very long. Some deep-sea jellies can be surprisingly big. They're not prehistoric dinosaurs, but they are strange, and they are real, and they are often overlooked. Then there's the matter of sound. The deep ocean is full of sound. Some of it is natural, some of it is human-made, some of it is still unexplained. There have been strange recorded noises in the ocean, like the famous bloop, which was once thought to possibly be biological. Later it was linked to ice-related events, but it captured people's imaginations for a reason. Because sound travels far in water, and in a place where you can't see, hearing becomes a form of knowing. Many deep-sea creatures rely on sensing vibrations. Some fish can detect pressure changes. Some animals can feel movement through the water, so if there were a large animal down there, it might be heard before it is seen. But hearing is tricky. The ocean is big. Sound sources can be far away. The same noise can have different causes. Still, the idea of something large moving in the dark is hard to ignore, because it's the kind of thought your brain doesn't easily let go of. Now, let's ground this again. The Mariana Trench is not a dinosaur zoo, but it is a place where ancient lineages can survive. It is a place where strange adaptations can thrive. It is a place where humans have barely looked. And it is a place where the ocean's ability to hide things is at its strongest. So what might be hiding there? If we stick to what is scientifically plausible, the most likely prehistoric creatures aren't extinct dinosaurs. They are living fossils, ancient lineages, deep-sea relatives of animals that have been around for ages. They might be unusual sharks in deeper zones than we've studied. They might be deep-sea fish with body plans that resemble ancient forms. They might be cephalopods that rarely come near our cameras. They might be crustaceans that have grown large in the cold darkness. They might be creatures so different from surface life that we wouldn't even recognise them as familiar categories at first glance. And it's also possible that the most prehistoric thing down there is not a single creature, but the entire environment. A world that still resembles what Earth's oceans were like long before humans ever existed. Cold, dark, pressurized, quiet. A world where survival depends on patience, and where time itself seems to slow down. Because in the deep sea, life often moves slowly. Growth can be slow, reproduction can be slow, metabolism can be slow. Some deep-sea animals live long lives, some may live longer than we expect, and that long, slow pace gives them an ancient feeling, like they're not rushing to meet deadlines or check notifications. They're simply existing in a steady rhythm in the dark, which is, in a strange way, comforting. It reminds you that the planet has layers, not just physical layers of rock and water, but layers of time. The surface world is loud and bright and fast. The deep world is quiet and old, and the Mariana Trench is one of the deepest layers we have. So as we begin this descent, it helps to let go of the Hollywood version of prehistoric creatures. The trench doesn't need that. The reality is already strange enough. Instead, imagine this. A place where pressure could crush steel. A place where the temperature hovers near freezing. A place where the only light comes from living things. A place where food falls from above like rare gifts. A place where life has had millions of years to adapt in isolation. And now imagine that in such a place, there might be creatures we haven't catalogued yet. Not because they're magical, not because they're impossible, but because we simply haven't looked closely enough. And that's the thought we'll carry with us as we go deeper into this story. Not fear, not fantasy, just curiosity. Because the deep ocean is still the biggest wilderness on Earth, and wilderness, by definition, is full of surprises. Now, to understand what could be hiding in the Mariana Trench, we need to understand what kind of world it is, and how it shapes everything that lives there. Not just in a general way, but in the very practical sense of what survives, what fails, and what never even gets the chance. So let's take a careful look at the trench itself, what it is, how it formed, and why it remains one of the most extreme environments our planet has to offer, even compared to other deep places in the ocean. If you've ever stood at the edge of the sea and looked out across the surface, it can feel like you're staring into something endless. The water stretches to the horizon, calm or restless depending on the day, and from up here it almost looks simple, blue, reflective, familiar. But the ocean is one of those things that behaves politely on the outside while hiding something enormous underneath, because the surface is only the skin. Beneath it, the world drops away, first gradually, then steeply, and then in places like the Mariana Trench, it falls into a depth so extreme that it stops feeling like deep water and starts feeling like a different planet that happens to be attached to ours. The Mariana Trench sits in the western Pacific Ocean, east of the Philippines and south of Japan, near the island of Guam. If you pulled up a map and traced the curve of it, it would look like a long, crescent-shaped wound in the Earth's crust. Not dramatic in colour, not glowing or marked by warning signs, just a feature in the seafloor that most people will never see. And yet, it's the deepest known place on Earth. When people say deepest, they usually mean something like the bottom of a lake or a swimming pool, or the part of the ocean where it gets cold and you can't see your feet anymore. But the trench isn't that kind of deep. It's not, I can't touch the bottom deep. It's, the bottom is almost 11 kilometres down deep. That number can be hard to picture because your brain doesn't have a good reference point for it. We don't live our lives measuring vertical distances in kilometres. We don't look down from our front porch and think, yes, that's about 9,000 metres. So here's one way to make it real. If you took Mount Everest, the tallest mountain on Earth, and lowered it into the Mariana Trench, it would not stick out of the water. The peak would still be submerged. There would still be water above it. That's not just deep. That's ridiculous. And the deepest known point inside the trench is called Challenger Deep. It's named after the British ship HMS Challenger, which conducted scientific surveys in the 1870s. At the time, the idea that the ocean could be that deep was almost unsettling. People already knew the sea was vast, but the trench made it personal. It made it measurable. It turned the ocean is big into the ocean is bigger than your mind is comfortable admitting. Challenger Deep is often described as being around 10,900 metres deep, give or take depending on the measurement method, and that give or take matters because measuring the deepest part of the ocean is surprisingly difficult. The ocean isn't still, the seafloor isn't perfectly flat. Equipment behaves differently under pressure. Sound waves travel differently depending on temperature and salinity. Even the act of trying to measure the bottom is like trying to take a ruler and measure the inside of a storm, but the exact number, while fascinating, is not the main point. The main point is that the Mariana Trench is so deep that it changes the rules. Down there, everything is different. The physics is different. The biology is different. The way life survives is different. And if you want to understand why the trench is such a tempting hiding place for creatures that feel prehistoric, you have to understand what kind of environment it is. Not in a poetic way, not in a mysterious abyss way, but in the practical sense of what happens to matter and living tissue when you go that far down. Because the Mariana Trench isn't just dark, it's crushing, it's cold, it's isolated, and it's huge. One of the most important things about the trench is that it isn't just a single pit, like a hole someone drilled into the earth. It's part of a long geological feature created by plate tectonics. The surface of our planet is made of large plates of crust that move slowly, like heavy pieces of broken shell drifting on a thick layer beneath. Most of the time, they move so slowly we don't feel it. But the movement is constant, and where those plates meet, things happen. Sometimes they grind past each other and create earthquakes. Sometimes they pull apart and create new crust. And sometimes one plate slides under another. That process is called subduction. The Mariana Trench exists because the Pacific Plate is being pushed under the Mariana Plate. The seafloor bends downward, deeper and deeper, until it forms the trench. Over millions of years, that bending becomes extreme. It becomes a boundary where the Earth's crust is literally being recycled back into the planet. So the trench is not just a deep spot. It's an active edge of the world, a place where the planet is still moving. And that matters because it means the trench isn't just cold and still and quiet. It's also a place of tension, a place where earthquakes can happen, a place where geological forces are constantly shaping the landscape, even if the changes are too slow for us to notice in a single lifetime. Now, if you could somehow ride a submersible down into the trench, the first thing you'd notice is the light disappearing. The ocean doesn't stay bright for long. Sunlight can penetrate the upper layers, but it fades quickly. The first zone is the epipelagic, the sunlit zone, where most of the ocean's photosynthesis happens. This is where plankton live, where fish schools shimmer, where the surface world still feels connected to the sky. Then you go deeper, into the twilight zone, where light is dim and blue and fading. It's still there, but it's not enough for plants. Shadows stretch strangely, colours change, red disappears first, everything becomes muted. Then you reach the midnight zone, where sunlight no longer exists. Not barely, not a little, none. It's gone completely. At that point, the ocean is not a place you see, it's a place you sense, and the Mariana Trench goes far below even that. The trench belongs to what's called the Hadal zone. The name comes from Hades, the underworld of Greek mythology, which is fitting, but it's also a reminder of how little we've explored it. The Hadal zone begins around 6,000 metres down, and it includes the deepest trenches on Earth. It's one of the least studied habitats on the planet, and it's not because scientists don't want to study it, it's because it's hard, it's expensive, it's risky. Equipment fails, pressure destroys things, cameras go dark, communication is difficult. Even getting a sample without crushing it or contaminating it can be a challenge. So the Hadal zone remains in many ways an unfinished chapter in human knowledge, which means it remains a perfect setting for unanswered questions. Now let's talk about pressure, because pressure is the trench's most brutal feature. At sea level, you live under one atmosphere of pressure. It's the weight of the air above you. You don't feel it because your body is built to handle it. You've lived with it your entire life. It's normal. But underwater, pressure increases rapidly. For every 10 meters you descend, you add roughly 1 atmosphere of pressure. That means at 100 meters down, you're at around 11 atmospheres. At 1,000 meters, you're around 101 atmospheres. And at the bottom of Challenger Deep, you're over 1,000 atmospheres. That's not a small difference. That's not a bit heavier. That's a completely different physical reality. If you took a human body and placed it at that depth without protection, it would be crushed almost instantly. Not slowly squeezed, not painfully compressed over time, just destroyed. The airspaces in your lungs, your sinuses, your body cavities, all of it would collapse. Your tissues would be forced inward. It would be immediate. Even metal struggles down there. Not because metal is weak, but because the pressure is relentless. Submersibles have to be built like armoured spheres. They can't have large flat surfaces because pressure would push them in. They need thick walls. They need careful engineering. And even then, the margin for error is small. The trench is a place where mistakes don't get a second chance. Now here's the strange part. Life exists there anyway. That fact alone should bother you a little, in a healthy way. Because it means living things have found ways to survive in conditions that would destroy us instantly. But they don't survive by being stronger, in a simple sense. They survive by being adapted. Their bodies are built for pressure, their proteins are stabilized, their membranes are structured differently, their chemistry is tuned to the deep. They are not visitors, they belong there. And when you think about what that means, it changes the way you picture the trench. It's not an empty pit, it's not a lifeless grave. It's a functioning ecosystem that has been operating for a very long time. The cold is another constant. Down in the Hadal zone, the temperature is near freezing, usually just a few degrees above 0 Celsius. It's not the kind of cold that comes and goes. It's not seasonal, it's steady. It's always there. Cold slows down biological processes. It slows metabolism. It slows growth. It slows movement. And that slowness becomes part of trench life. Many deep-sea animals grow slowly. Some live long lives. Some have low-energy lifestyles because burning energy quickly in a place with scarce food is a bad plan. So the trench isn't just deep and dark. It's also slow. That matters when we talk about prehistoric feeling creatures, because prehistoric often means something that feels older, slower, less frantic. Something that looks like it belongs to a world before humans made everything loud. And the trench fits that. But it also has another feature that makes it a frontier: isolation. The Mariana Trench is not connected to the surface world in the way a shallow reef is. Down there are no storms, no waves, no sunlight, no coral forests, no floating algae, no daily rhythms of bright morning and dark night. The trench is cut off from the surface in a way that's hard to imagine. It's like living at the bottom of a canyon so deep that the sky might as well not exist. And because it's isolated, it can become a place where evolution takes unusual paths. On the surface, ecosystems are connected. Species migrate, genes flow, environments shift, competition is constant. Predators and prey co-evolve quickly. In the trench, the environment is stable, and the barriers to movement are enormous. That can allow certain lineages to persist for long periods. It can also allow strange specializations to develop. You could think of it as a set of biological islands, except instead of being surrounded by water, they're surrounded by depth. Now, there's another important part of the trench story, and it's one people don't always like to think about. The trench is not clean. Even in the deepest part of the ocean, humans have left traces. Plastic has been found in the Mariana Trench. Chemical pollutants have been found there too. The idea that the deepest place on Earth has plastic in it is the kind of fact that makes you go quiet for a moment. Because it means there is no true away. There is no place where we can throw things and pretend they disappear. But the trench also functions as a kind of collection point. It gathers what sinks. It gathers debris. It gathers the dead remains of surface life. It gathers particles drifting down. It's not just a deep place, it's a deep place that accumulates, and that accumulation is part of what supports life down there. Which leads us to the next major question. What do trench creatures eat? Because without sunlight, you don't have plants. Without plants, you don't have the normal base of the food chain that most surface ecosystems rely on. Instead, the trench depends heavily on what's called marine snow. Marine snow is a gentle, constant rain of organic material falling from the surface. Dead plankton, tiny bits of tissue, waste, mucus, fragments of decaying life. It sounds unpleasant, but it's the main source of food for many deep-sea ecosystems. If you've ever shaken a snow globe and watched the particles drift down slowly, that's the basic visual, except instead of glitter, it's the leftovers of a life. And in the trench, marine snow is both essential and unreliable. Some days, it might be more abundant, other times, less. It depends on what's happening above. Plankton blooms, seasonal changes, ocean currents, storms, death events. So the trench is a place where food arrives from the sky, but the sky is thousands of meters away and you can't see it. That's a strange way to live. It's also a way of life that encourages scavenging, patience and opportunism. And those are traits that can make creatures seem ancient. Because scavenging is an old strategy. It's one of the earliest ways life can survive. If you can't hunt actively, you wait. If you can't rely on plants, you rely on whatever falls. Some trench animals do feed directly on the sediment, processing it to extract nutrients. Others are predators, hunting smaller animals. Some are both, depending on what's available. But in general, trench life is not about abundance. It's about making the most of very little. Now, when people imagine the Mariana Trench, they often imagine it as a narrow, sharp crack in the earth, a vertical drop like the edge of a cliff. In reality, the trench is more complex. It has slopes, it has ridges, it has terraces, it has different habitats depending on depth and location. The walls can be steep in some places, gentler in others. The bottom is not a smooth, flat line. It's varied terrain. That variety creates microhabitats, places where certain animals can live while others can't, places where sediment collects differently, places where currents behave differently, places where food accumulates. And that matters because when you're searching for unknown creatures, the terrain matters. You don't just look in the trench, you look in the right parts of it. Some animals might live on the slopes, where more food might drift down and get caught. Some might live on the bottom, where sinking material settles. Some might live in the cracks and crevices of the trench walls, and some might live in places we haven't sampled at all. Because even if we've sent a few submersibles down there, that doesn't mean we've explored it thoroughly. A handful of dives does not equal knowledge of an entire ecosystem. Imagine trying to understand the Amazon rainforest by walking into it for 20 minutes and then leaving. You might see a few insects, a bird, some plants. You would not come back claiming you had catalogued everything. The trench is like that, except it's darker, colder, and it can crush your equipment. Now, let's talk about what it feels like to actually go down there, because the human relationship with the trench is part of what makes it feel like a frontier. Humans have always been drawn to edges, the edge of the map, the edge of the forest, the edge of space. We like the idea of going somewhere that feels unknown, and the Mariana Trench is one of the last unknown edges on Earth. When explorers first reached deep oceans, they had limited tools. Early oceanographers used weighted lines to measure depth, lowering them until they hit bottom. That method worked for shallow areas, but in the trench it becomes absurd. The line would have to be miles long, the weight would swing, currents would drag it. Eventually technology improved. Sonar allowed scientists to map the seafloor using sound waves. Ships could send pulses down and measure how long it took for them to return. That gave a clearer picture of the trench's shape. But mapping is not the same as seeing. To see the trench, you need to go there, and going there is difficult. There have been only a small number of crewed descents to Challenger Deep. Jacques Piccard and Don Walsh reached it in 1960, in the Bathyscaphe Trieste. They were down there for a short time, but the fact that they reached it at all was astonishing. It was a reminder that humans can force their way into environments that don't want them. More recently, other missions have reached the bottom, including filmmaker James Cameron in 2012, who made a solo dive in the Deep Sea Challenger submersible. There have also been uncrewed vehicles, robotic explorers, landers and sampling missions. But even with all that, the trench remains mostly unvisited. And that's why it's still a frontier. Not because it's completely untouched, but because our contact with it is minimal compared to its size and complexity. It's like we've knocked on the door a few times, peeked inside, and then left. Now, there's another reason the trench is a frontier, and it's a reason that connects directly to our main topic. The trench is a natural hiding place. If a creature wanted to avoid being seen, the trench is ideal. Humans don't live there. Humans don't swim there. Humans don't fish there, not directly. We don't send nets to the bottom of Challenger Deep. We don't build underwater cities there. We don't casually explore it. We barely touch it. And that means if a lineage of animals has survived down there, it could remain unknown for a long time, especially if it's rare. Especially if it doesn't come to bait. Especially if it avoids noise and light. Especially if it lives in pockets of the trench where we haven't placed cameras. Now, the idea of prehistoric creatures in the trench often triggers a certain mental image. Something big. Something toothy. Something that feels like it should have gone extinct a long time ago. But the trench doesn't necessarily favour giant predators. It favours creatures that can survive with limited food. So if there are ancient survivors down there, they might not be massive. They might be small and strange and perfectly designed for their environment, and that can be even more unsettling in its own quiet way. Because it suggests that the trench isn't waiting for us with one dramatic monster. It's filled with countless small forms of life, each one adapted to an extreme world, each one potentially carrying ancient traits, ancient chemistry, ancient strategies. Some of them might resemble creatures from long ago. Some of them might be entirely new, and some might be so unusual that we don't even know how to classify them properly yet. This is where the trench becomes more than a geographic feature. It becomes a reminder that we don't fully know our own planet. We know the surface, we know the continents, we know the skies, we've walked on the moon. But beneath the ocean, there is a world that is still largely unmapped in the way that matters most. Not in lines and measurements, but in living things. So when we call the Mariana Trench Earth's darkest, deepest frontier, it's not just a dramatic label, it's accurate. It's a frontier because it is physically extreme, difficult to reach, and still full of unknowns. And the deeper you go, the more those unknowns multiply. Because the trench isn't just deep, it's layered. The conditions change with depth, the pressure increases, the food availability shifts, the terrain changes. So the animals change too. Some creatures might live at 6,000 meters and never go deeper. Others might live at 8,000 meters and never come up. Some might be found only in the deepest parts, where pressure is highest and life becomes even more specialized. And that specialization is what makes the trench so interesting when we talk about prehistoric survivors. Because specialization can preserve ancient forms. It can also create new forms that look ancient because they're stripped down to basics. When you remove sunlight, remove warmth, remove easy food, remove shallow water, you don't get cute reef fish. You get animals that are built for survival. That's the trench's signature. Survival. Now, as we continue, we need to address something important. The Mariana Trench is not just a mysterious place because it's deep. It's mysterious because the deep ocean doesn't behave like the surface world. The surface world is ruled by sight. We see threats. We see food. We see shelter. We see each other. In the trench, sight is optional. Down there, darkness is permanent. So other senses matter more. Touch, vibration, chemical sensing, pressure detection, the ability to detect tiny changes in the water, and that means the creatures down there are built differently. Some have large sensory organs, some have long antennae, Some have strange structures that help them feel the world rather than see it. Some produce light. Bioluminescence is one of the most famous deep-sea traits, and while the trench itself may have less bioluminescence than some other deep zones because of energy constraints, light in the deep ocean is still a major theme. Light is used for communication, for attracting prey, for confusing predators, for camouflage. In the deep, light becomes language. And when you imagine a world where the only light comes from living things, it changes how you picture the environment. It's not just blackness. It's blackness interrupted by small flashes, faint glows, drifting sparks. That kind of environment can make any creature feel like it's from another era, because it's not the world we evolved to live in. Now, let's bring this back to the core question. If the Mariana Trench is Earth's deepest frontier, what does that mean for the idea of hidden prehistoric creatures? It means the trench has 3 key ingredients for long-term secrecy. First, extreme conditions. Few creatures can survive there, so the ones that do are specialised and often isolated. Second, low human presence. We don't spend time there. We don't casually explore it. We don't live there. Our ability to observe it is limited. Third, a vast environment. Even though the trench is a specific feature, the deep ocean around it is enormous. The trench connects to slopes and nearby deep areas. It's part of a larger deep-sea world that covers most of the planet. If something exists in that world, it can remain hidden simply because there's so much space to hide in. And this is where the idea becomes less like fantasy and more like probability. Not the probability of one specific monster, but the probability that there are still species we haven't identified, that there are still animals down there that don't appear in our books, that there are still lineages surviving in pockets we haven't sampled, that there are still deep-sea ecosystems that operate without our knowledge. Because if you look at how often we discover new species even in relatively accessible places, it's not hard to imagine that the deep ocean holds many more. Now, to go further into this, we need to answer another question. Why does the deep ocean feel prehistoric in the first place? Why does it trigger that specific kind of fascination, where people imagine ancient creatures lurking in the dark? It's not just because it's deep, it's because the deep ocean has a different relationship with time. On the surface, everything changes quickly. Seasons, weather, temperatures, light, food. In the deep, the conditions are stable. Cold and dark, year after year, century after century. That stability can preserve old forms of life. It can also slow down evolution in some ways because the environment isn't constantly shifting, and it can create the impression that the deep is an older world, running on older rules. So as we continue this descent, the next step is to explore that feeling more directly. Not as a mood, but as a scientific reality. Because the deep sea really does preserve ancient traits, ancient body plans and ancient survival strategies. And once you understand why, the idea of hidden prehistoric creatures becomes less about imagination and more about what the ocean has already proven it can do. When people say the deep ocean feels prehistoric, they usually don't mean it in a casual way, like calling an old building ancient because it has creaky stairs. They mean it with a kind of instinctive seriousness, a feeling that the deeper you go, the more the world starts to resemble a time before humans, before cities, before anything familiar. It's the sense that you're drifting backward through the history of life, not because the deep is literally stuck in the past, but because it carries clues from the past in a way the surface world doesn't. And that feeling isn't just imagination doing its usual late-night work. There are reasons the deep ocean gives off that prehistoric impression. Some are biological, some are geological, some are psychological. All of them stack together until the deep starts to feel like a living museum that never closes, except it's not neat and labelled and brightly lit. It's dark, it's cold, it's huge. And it doesn't care that we're curious. One of the simplest reasons the deep ocean feels prehistoric is that it changes slowly. The surface world is loud with change. Weather moves fast, temperatures shift daily, storms rearrange coastlines, seasons redraw the landscape, Fires burn forests. Ice ages reshape continents. On land, if you blink on a geological timescale, everything can look different. Even in the shallow ocean, conditions change quickly. Sunlight rises and falls, water warms and cools, waves stir sediment, algae blooms appear and vanish, fish migrate, predators follow, reefs can grow, bleach, recover, break, and rebuild. But in the deep ocean, many of those drivers of change are absent or muted. There's no sunrise, there's no seasonal light cycle, the temperature stays near freezing, there are no waves crashing, no hurricanes stirring the bottom, no warm, shallow nurseries rapidly shifting year to year. It's stable, not perfectly, not forever, but stable enough that life can settle into long-term strategies. In stable environments, organisms don't always need to reinvent themselves. They can keep what works. And when what works happens to be a body plan that's been around for tens or hundreds of millions of years, you end up with creatures that look like they could have swum alongside ancient seas. That's the first ingredient. Slow change creates long continuity. The second ingredient is that the deep ocean holds lineages that are genuinely old. Some groups of animals have been in the ocean for a very long time, not metaphorically, literally. Sharks have been around for over 400 million years. Horseshoe crabs, which aren't true crabs but their own ancient branch, trace back hundreds of millions of years too. Nautiluses have relatives in the fossil record that go back to before dinosaurs existed. Coelacanths, as we've already touched on, represent a lineage thought to be extinct until one turned up alive. Not all of these live in the Mariana Trench, but they're part of the same story. The ocean, especially deeper parts of it, can act as a refuge for ancient lineages. The environment doesn't force rapid reinvention in the same way. Predators and competition exist, but the pace can be different. When you see a deep-sea creature that looks strange or ancient, sometimes it really is a close cousin of something that existed long ago. Not always unchanged, but carrying recognizable features that have survived across enormous spans of time. Then there's another reason the deep feels prehistoric, and it's one we don't often admit out loud. We don't know it well. The unknown always feels older. If you think about human history, the places we didn't understand were often described in mythic terms. Deep forests, vast deserts, polar regions, mountain peaks, the open sea. They were called wild, mysterious, untamed, not because the land was actually more magical, but because it wasn't mapped and domesticated in our minds. The deep ocean is one of the last major places on Earth where that is still true. We have maps of the seafloor, yes, but a map is not knowledge in the way living observation is knowledge. Knowing the shape of a mountain is not the same as knowing what lives in every crevice. You can trace the trench on a chart and still have no idea what's moving through its water, what's crawling across its bottom, what's drifting along the slopes. So our brains do what they always do when faced with a blank space. We fill it with older images, fossils, monsters, ancient survivors. It's not childish, it's human. But the deep ocean doesn't just feel prehistoric because it's unknown. It also feels prehistoric because it looks, behaves, and sounds different from our world. Even the basic mechanics of living down there are unfamiliar. On the surface, life is shaped by sunlight. Plants grow, herbivores graze, predators hunt. The energy is direct. The food chain begins with photosynthesis. The whole system is built on light. In the deep, sunlight is gone, so the system has to be built differently. Many deep ecosystems rely on what falls from above. That means life is shaped by scarcity, patience, and opportunism. It's a lifestyle that can resemble earlier stages of life's history, when ecosystems were simpler and energy was less abundant. And in some deep places, there's another source of energy that feels like something from the early Earth: chemosynthesis. Hydrothermal vents, cold seeps, and other chemically rich environments allow microbes to produce energy by using chemicals like hydrogen sulfide or methane, rather than sunlight. This is not the main food base for the Mariana Trench in most areas, but it's part of the broader deep ocean world, and it's one of the strongest reasons the deep feels ancient. Because chemosynthesis may resemble how life survived before the surface was rich with oxygen and sunlight-driven ecosystems. Some scientists consider vent ecosystems to be analogues for early Earth environments. They are places where life thrives around chemicals and heat, in darkness, using metabolic pathways that don't require the sun. When you watch footage of hydrothermal vent communities, it's hard not to feel like you're looking at a planet in its early stages. Tube worms, strange crustaceans, microbial mats, clouds of mineral-rich water billowing like underwater smoke. It looks like the world is still being built. That isn't nostalgia. That's geology and biology blending together in a way that reminds you how old Earth is. Now, the Mariana Trench itself isn't full of blazing hydrothermal vents, the way some mid-ocean ridge systems are, but the trench is part of a subduction zone. Subduction zones can have hydrothermal activity and seeps in some regions. Even when you don't have dramatic vents, you still have geological processes shaping the chemistry of the seafloor. And chemistry matters, because it can create pockets where unusual organisms thrive. If you ever wonder how something prehistoric could persist, chemistry is part of the answer. An isolated pocket of conditions can act like a shelter. A stable chemical environment can support microbes that support larger organisms. A trench can trap organic material, concentrate nutrients and maintain cold stability. This is how ecosystems become refuges. Another reason the deep feels prehistoric is the look of the animals themselves. Deep-sea creatures often have features that seem exaggerated or primitive, depending on how you look at them. Big teeth, huge mouths, small eyes or no eyes, long, thin bodies, gelatinous forms, hard armour, strange sensory appendages. Some of these features are adaptations to darkness and scarcity. Others are just the result of deep-sea evolution, taking paths that feel unfamiliar to surface eyes. The problem is that our brains have expectations. We're used to animals shaped by light. We're used to camouflage patterns we can see. We're used to sleek shapes that move through shallow water. We're used to ecosystems where food is abundant enough to support constant movement. When we encounter an animal that doesn't fit those patterns, we label it as alien, ancient, or both. Take the deep-sea anglerfish, for example. It uses a bioluminescent lure to attract prey. It has a mouthful of teeth. It can swallow prey larger than itself. It has a body that looks like it was built to survive in perpetual hunger. Does it feel prehistoric? To many people, yes. But what you're really seeing is specialization. A creature shaped by an environment where prey encounters are rare. When you only get occasional chances, you need to be ready to make the most of them. So the anglerfish looks dramatic because its survival strategy is dramatic. The same is true for many deep-sea predators. Dragonfish, Viperfish, gulper eels. They often look like they belong in a museum display labelled Ancient Sea Monster, but they are modern animals with modern evolutionary histories. They just happen to inhabit a world that rewards extreme features. Now let's talk about the pace of life, because prehistoric isn't just about appearance, it's also about movement. On land, you see animals moving quickly. Birds dart, mammals run. Insects buzz. Even plants respond fast compared to deep ocean time. In the deep, movement can be slower. Not always, but often. That's partly because cold water slows metabolism, and partly because food scarcity makes wasting energy dangerous. Some deep-sea animals may go long stretches without eating. Some may feed on whatever drifts down. Some may be opportunistic hunters that wait rather than chase. This kind of patience feels old to us because it runs against our surface world tempo. It's like watching a world where everything has been told to calm down and conserve its energy. And that slow, steady rhythm can make the deep feel like a place where time itself behaves differently. That brings us to another factor, longevity. Some deep-sea animals live very long lives. The Greenland shark is the headline example, with estimates suggesting it can live for centuries. Deep-sea corals can live for thousands of years. Some deep-sea sponges may be extraordinarily old. Even if an animal's body plan isn't ancient, its lifespan can give it an ancient presence. When you think of a shark that might have been alive when your great-great-great-grandparents weren't even born, you start to understand why the deep feels like a different era. And longevity in the deep isn't just a fun fact, it's part of why certain lineages persist. Long-lived organisms can maintain populations in low-energy environments. They don't need rapid reproduction. They can endure. Endurance is one of the deepest prehistoric themes there is. Now, there's another reason the deep feels prehistoric, and it's one that sits quietly in the background of everything we've said so far. The deep ocean is the oldest continuous habitat on Earth. Land environments have changed drastically over time. Continents rise and fall, seas flood and retreat, glaciers advance and melt, forests shift. But the deep ocean has existed for a very long time as a habitat. Its basic character, cold, dark, pressurized, has been stable across huge spans of time. That doesn't mean the deep ocean today is identical to the deep ocean 300 million years ago, but it does mean there has always been deep ocean. There has always been a place where light doesn't reach, where pressure is high, where temperature is low. So while surface ecosystems have been wiped out and rebuilt repeatedly by mass extinctions, climate shifts, and geological upheaval, the deep has often acted as a buffer. It's not immune to change, but its changes can be slower and less chaotic. This is one reason some scientists consider deep sea habitats to be potential refuges during extinction events. If the surface becomes hostile, deep environments may remain more stable, not always safe, but sometimes safer. And if a lineage can survive a mass extinction by retreating deeper, or by already living deep, then it can carry traits from earlier eras into the present. That's how you get animals that look like ghosts from older chapters of Earth's history. Now, when we focus on the Mariana Trench specifically, we should keep in mind that the trench is not the only deep place, but it is one of the most extreme. The Hadal zone is a specialized slice of deep ocean habitat. It's like the deep sea turned up to maximum. And in such an extreme habitat, you see extreme adaptations. Sometimes that means creatures look simpler and more primitive, because complex features aren't helpful down there. You don't need bright colours if there's no light. You don't need speed if there's no constant food. You don't need thick bones if pressure punishes rigid structures. So you can get animals with soft bodies, reduced skeletons, minimal eyes, and sensory systems tuned to pressure and vibration. To a surface human, that can look like an older, more basic design, which is another reason the deep feels prehistoric. But we should also address a subtle misunderstanding people often have. Prehistoric does not mean unchanged. When we talk about living fossils, it's tempting to imagine a creature that has stayed exactly the same for hundreds of millions of years. In reality, evolution doesn't stop. Even if a creature looks similar to its ancient relatives, its genetics have changed, its physiology has adapted, its behaviours have shifted, it has evolved. What makes it feel prehistoric is that the overall body plan has remained recognisable. The basic design still works, so the deep ocean isn't a frozen museum, it's a working system that happens to preserve certain designs because they remain effective. Now, there's one more reason the deep feels prehistoric, and it's not about biology or geology. It's about the way we, as humans, relate to it. We are surface animals. Our ancestors evolved in sunlight, on land, in air. Even when humans became coastal and began using the sea, we remained tied to the surface. We sail above the water, we fish from above, we dive briefly and come back up. We don't belong in the deep, and whenever we encounter an environment we don't belong in, it can feel ancient. It can feel like a reminder that the world existed long before we did, and it will exist long after. The deep ocean doesn't acknowledge us. It doesn't make room for us. That indifference feels old. It feels like stepping into a cathedral built by time itself, where you are not the focus. Now hold on to that thought because it sets up something important. If the deep ocean feels prehistoric because it is stable, because it contains ancient lineages, because it runs on different energy systems, because it moves slowly, because it's vast and unknown, then the idea of hidden prehistoric creatures becomes less of a fantasy and more of a question about probability. Not, is there a dinosaur down there, but what kinds of lineages could persist in a place like this without us noticing? And before we even name specific candidates, we need to talk about the biggest constraint of all, pressure. Because pressure is not just a danger to humans, it shapes what life can be, it sets boundaries, it determines which kinds of bodies can exist at those depths and which cannot. So the next step is to get practical about the environment itself, what it does to living tissue, how animals handle it, and why the trench is not simply an empty pit, but a world where survival requires a very specific set of solutions. If the Mariana Trench had a personality, pressure would be its sharpest feature. Darkness is dramatic, cold is unsettling, isolation feels eerie, but pressure is the one that makes the trench feel actively hostile. It's the part that turns the deep ocean from mysterious into physically impossible, at least from a human point of view. Because pressure down there is not a small inconvenience. It is not a detail you can ignore while you focus on the interesting animals. It is the defining condition. It is the rule that everything must obey. And when you first learn what that rule looks like in numbers, the natural reaction is to assume life can't handle it, that a world under that much weight must be sterile, empty, quiet, a place where nothing moves because nothing can survive, but life does survive. Which means the real story isn't that pressure makes survival impossible, it's that pressure forces life to become something else, something built for a world we were never meant to enter. Pressure is, at its core, just force spread over an area. At sea level, you live under the pressure of the atmosphere. The weight of all that air above you presses down with about 101,25 pascals, which is called 1 atmosphere. It sounds technical, but it's basically the background pressure your body has always experienced. Your tissues, your blood, your lungs, your bones, all of it is balanced against that pressure. You don't feel it because the inside of you pushes back. Underwater, pressure climbs rapidly because water is dense, much denser than air. Every meter you descend adds more weight of water above you, and that weight presses on everything. A rough rule is that pressure increases by 1 atmosphere for every 10 meters of depth. So at 10 meters, you're at about 2 atmospheres, at 50 meters, about 6, at 100 meters, about 11. You can feel that even as a diver. Your ears pop, your chest feels tighter, you have to equalize, your body notices. Now take that rule and apply it to the Mariana Trench. At 1,000 meters, you're around 101 atmospheres. At 5,000 meters, around 501 atmospheres. At the deepest parts, near 11,000 meters, you're over 1,100 atmospheres. That means the water is pressing down with a force of more than 1,000 times what you experience at sea level. A useful way to picture it is to imagine stacking weight on a single point. At the bottom of Challenger Deep, the pressure on your body would be similar to having dozens of jumbo jets stacked on top of you. Not balanced carefully, just dropped. The result is not slow crushing, it's immediate collapse. That is why submersibles have to be built like armoured pressure vessels. They aren't shaped like normal boats. They're often spherical or rounded because curves distribute pressure more evenly. Flat surfaces are dangerous. A flat window, for example, would have to be incredibly thick, and even then it could fail. If you watch footage of deep-sea submersibles, you'll notice they look less like vehicles and more like carefully engineered capsules designed to resist the ocean's desire to push everything into a smaller shape. And this is the first clue about how life survives. Resistance isn't always the strategy. Humans try to resist pressure by building strong shells. Many trench creatures survive by not having anything for pressure to crush in the first place. That might sound strange, so let's break it down. Pressure is most dangerous when there are pockets of gas or empty space, because those spaces collapse under pressure. That's why your lungs are the most vulnerable part of your body underwater. They are filled with air. Under enough pressure, they compress. If the pressure change happens too fast, tissue can tear. If the pressure is extreme, the structure simply collapses. In the deep ocean, animals don't carry large gas-filled spaces. Most deep-sea fish don't have the same kind of swim bladder you see in shallow fish. A swim bladder is basically a gas-filled sac that helps a fish control buoyancy. In the deep, that's a problem, because gas compresses. So many deep-sea fish either have reduced swim bladders, oil-filled structures instead, or they rely on other ways to maintain buoyancy, like gelatinous tissue. They can be neutrally buoyant without needing a balloon inside them. That's one of the reasons deep fish often look soft. Their bodies can contain more water and less dense tissue, making them float without needing gas. And softness is not weakness in that environment. It's a solution. If you have a body that is mostly the same density as the surrounding water, pressure affects you differently. The pressure is still there, but there's no big mismatch between inside and outside that creates a crushing gradient. Everything is being pressed equally. That's one of the most important ideas to understand. Pressure itself isn't always lethal if the organism is built to be in balance with it. But balance doesn't solve everything. Pressure still affects chemistry. It affects how proteins fold. It affects how membranes behave. It affects how molecules interact. And this is where trench life becomes genuinely impressive, because at these pressures, the machinery of life can break. Proteins are the workhorses of biology. They are molecules folded into specific shapes that allow them to do jobs like building tissue, transporting oxygen, copying DNA, processing food, and sending signals. Their shape matters. If a protein folds wrong, it may not work. High pressure can distort protein folding. It can push proteins into different conformations. It can alter chemical reactions. It can affect enzyme activity, which means basic metabolism can fail if the chemistry isn't adapted. Cell membranes too are affected. Membranes are made of lipids, and their fluidity matters. If a membrane becomes too rigid, it can't function properly. If it becomes too fluid, it leaks. Pressure can change how lipids pack together, altering that fluidity. So trench organisms have to solve a chemistry problem that humans don't normally deal with. They do it with specialized adaptations. One of the key strategies involves small molecules that help stabilize proteins under pressure. These are sometimes called piezolites. A well-known example is TMAO, trimethylamine N-oxide. Many deep-sea fish and invertebrates accumulate TMAO in their tissues, and it helps counteract the destabilizing effect of pressure on proteins. There's a reason deep-sea fish can smell strongly of trimethylamine when brought to the surface. That smell is associated with breakdown products, and it's part of the chemistry that helps them survive down there. But here's an important constraint. TMAO can only increase so much before it becomes problematic. It affects osmotic balance. It can have other physiological costs. Scientists have suggested there may be an upper limit to how much TMAO a fish can accumulate, which might contribute to why fish are rarely found below certain depths. This is why the trench can be a world where fish exist, but not necessarily everywhere, and not in infinite variety. Biology has limits. Chemistry sets boundaries. And that leads us to a question that sits at the heart of the trench mystery. If pressure pushes life towards certain adaptations, does it also create a boundary beyond which complex animals cannot exist? In other words, is there a depth at which vertebrates, like fish, simply can't function? This isn't theoretical. It's a real question scientists study because when we survey the deepest parts, we see patterns. There are fish that live very deep, including trench snailfish that have been observed at depths exceeding 8,000 meters. But fish seem to become less common or absent in the deepest Hadal zones. In some studies, there appears to be a depth beyond which fish are not found. That doesn't mean nothing is there. It means the community shifts. Invertebrates like amphipods and worms may dominate the deepest zones. Why? Because invertebrates often have different physiological constraints. They don't have the same bone structures. They don't have the same metabolic demands. They can have different chemical tolerances. So the trench isn't simply a deeper version of the shallow ocean. It's a different category of habitat, with its own biological rules. And those rules matter when we speculate about prehistoric creatures. If someone imagines a massive reptile down there, a creature breathing air and swimming at the bottom, the physics and biology make that unlikely. Air-breathing animals need to surface. They need lungs. They need gas spaces. They need oxygen. Even whales, which can dive deep, cannot go anywhere near trench depths. Their bodies are remarkable, but not built for that pressure range. They have limits. So anything living in the trench full-time needs to be built for pressure. It can't be a surface animal simply hiding. It has to be a deep animal in its bones, chemistry and structure. Now another part of pressure's story is how it interacts with movement. At those depths, water is still water, but the environment is dense and cold. Moving requires energy. Many trench animals conserve energy by moving slowly, staying close to the bottom, and using strategies like scavenging or ambush rather than constant active hunting. But pressure also influences the mechanics of muscle and nerve function. Electrical signaling in nerves depends on ion channels, which are proteins embedded in membranes. If pressure affects membranes and proteins, it can affect nerve conduction. If nerve conduction changes, movement and sensation change. So trench animals often have nervous systems tuned to their environment. Their metabolism is often adapted to cold, which slows biochemical reactions. Their muscle composition can differ. This is why deep-sea footage often shows animals moving in a slow, deliberate way. Not always, but often. It's not laziness, it's survival. Now, pressure also creates a practical barrier for us, and this barrier affects what we know. The deeper you go, the harder it is to study anything. Equipment must resist pressure. Sampling devices must withstand crushing forces. Cameras must function in darkness and cold. Even if you can get a sample, bringing it to the surface changes everything. Pressure drops, temperature rises. The animal's body, built for a world of crushing pressure, may not survive decompression. Tissues can rupture. Chemistry can shift. Gas can expand in unexpected places. Many deep-sea organisms are damaged or killed by the very act of collecting them. That means our knowledge of trench life is biased toward creatures that can survive collection, or at least remain identifiable after collection. It also means that some organisms might remain unknown because we can't bring them up intact. To deal with that, scientists sometimes use pressurized containers that maintain deep-sea conditions during ascent. These systems are improving, but they're not easy. They're complex, expensive, and limited. So when you think about how little we know about the trench, pressure is part of why. It blocks us. It forces us to observe life from a distance. It forces us to rely on remote cameras, baited traps, and robotic explorers. And it means the trench remains a place where we have glimpses, not constant surveillance. Now here's where pressure becomes more than a technical detail. It becomes part of the trench's emotional effect. Pressure gives the trench weight, in a literal sense, but also in a psychological sense. It makes the deep feel final. It makes the environment feel uncompromising. When you imagine something living at the bottom of Challenger Deep, you're imagining a creature that has adapted to conditions that would instantly destroy you. That creates a kind of respect, even if the creature is small. It also creates a feeling of distance. Not just physical distance, but biological distance. Trench creatures are not just far away. They are built differently. They live by different rules. They belong to a different version of Earth. That's why the trench feels like a frontier. Now, to talk about prehistoric creatures hiding there, we need to be clear about what pressure allows and what it discourages. Pressure allows life that is flexible rather than rigid, chemically adapted rather than chemically ordinary, low energy rather than fast burning, often small or moderate in size rather than enormous, built without gas spaces, often living close to the bottom where food collects. Pressure discourages life that is dependent on air, dependent on rigid structures that can't tolerate compression, dependent on high energy consumption without reliable food, dependent on frequent movement over long distances. And this doesn't mean large animals can't exist in the deep ocean generally. Large squid exist in deep waters, large fish exist, whales dive deep. But the Hadal zone, the trench depths, is a different level of constraint. So if we imagine prehistoric survivors down there, we should imagine them as organisms that fit these rules. Perhaps ancient lineages of crustaceans that have adapted to pressure. Perhaps worms with traits that resemble ancient marine worms. Perhaps fish lineages that have specialized chemical systems to push deeper than we expected. Perhaps gelatinous organisms that don't rely on rigid structures. Perhaps things that don't look like the prehistoric we're used to, but still represent ancient strategies. Now, there's another way pressure shapes the trench environment, and it's not about the animals' bodies, it's about the habitat. High pressure affects how materials behave. It influences the solubility of gases. It can affect how certain chemical reactions occur in sediments. It can influence microbial processes. Microbes are the foundation of deep-sea ecosystems. In the trench, microbial life in sediments plays a major role in breaking down organic material. Those microbes can be pressure adapted too, called piezophiles. Some microbes actually grow better under high pressure. They are not just tolerating it, they prefer it. And microbial activity affects everything else, because microbes process the falling organic material. They recycle nutrients. They create chemical gradients that other organisms can exploit. So the trench is not simply a place where a few hardy animals survive. It's a place with microbial ecosystems that are comfortable under crushing weight. That's another reason life exists there. And it's another reason the trench can serve as a refuge. Microbes can thrive, which means the base of the ecosystem can persist even in extreme conditions. Now, if you're listening to all this and thinking, so pressure makes it impossible for anything big and dramatic to hide there, don't be too quick. Pressure sets constraints, but evolution can produce surprising solutions. The trench doesn't need a movie monster to be strange. It can be strange with creatures that are only a foot long, if they are built in ways that challenge your sense of what life should be. A trench snailfish, for example, may look soft and ordinary on camera, but its biology is extraordinary. It carries chemistry in its tissues that helps its proteins function under pressure. Its body is adapted to avoid crushing. Its entire existence depends on a world that would pulverize a surface fish instantly. That is dramatic, even if it's quiet. And here is the key point. Pressure is not just an obstacle. It is a filter. It shapes who gets to live there. It keeps most forms of life out. It selects for specific adaptations. It makes trench life rare, specialized, and often isolated. And isolation is the beginning of mystery. Because when populations are isolated, they can diverge. They can form unique species. They can develop unusual traits. They can survive in pockets without being seen. The trench, under its crushing weight, becomes a set of hidden habitats where evolution can do its work largely out of view. That's why the Hadal zone can hold surprises, not because it's magical, because it's selective. Now the next piece of the puzzle is this. If the trench has no sunlight and food is scarce, how does a whole ecosystem function at all? What keeps it going? What are the basic energy pathways that make life possible? Once we understand that, we'll have a clearer sense of which kinds of creatures could realistically persist, and why some kinds of prehistoric survival make more sense than others. If you remove sunlight from a world, you remove the most familiar source of energy life depends on. On the surface, sunlight is so constant and so normal that we rarely think of it as the foundation of almost everything. Plants take it in, convert it into chemical energy, and that energy flows outward through food webs like money moving through an economy. Herbivores eat plants, carnivores eat herbivores, scavengers clean up the leftovers, decomposers recycle what remains. It's a system that looks complicated when you zoom in, but at its base it's powered by light. So when you hear that the Mariana Trench is permanently dark, the obvious question is simple: what eats what? Because if there are no plants down there, and no photosynthesis, then where does the energy come from? How can anything survive at all? How can there be predators, scavengers, worms, fish, and entire communities in a place where the sun has never reached, and the answer is both elegant and slightly unsettling. Life in the deep sea doesn't break the rules, it follows them in a different direction, it finds energy where it can, and it becomes extremely good at using every scrap. The deep ocean is not a place where food is abundant, it's a place where food is precious. It arrives slowly, unpredictably, and often in forms that don't look like food the way we picture it on the surface. If you want to understand how deep-sea food webs work, you have to forget the idea of a lush base layer of plants. You have to replace it with something much more subtle, a constant rain of leftovers. This is where we begin with the concept that supports most of the deep ocean, including trench environments. Marine snow. Marine snow is not snow in the icy sense. It's called snow because it falls gently and continuously from the surface down into the dark. It's made of tiny particles of organic material, dead plankton, bits of decaying tissue, fecal pellets from animals feeding above, mucus from organisms, fragments of algae, tiny shells, cellular debris, all the loose biological matter that gets produced in the sunlit zone and then sinks. If you could float in the mid-water and watch it, you'd see small flecks drifting downward like dust in a sunbeam, except there is no sunbeam. It's just particles falling through darkness, slowly, patiently, always. And for deep-sea life, marine snow is a lifeline. It's not a feast, it's not a buffet, it's more like a steady supply of crumbs. But those crumbs are enough to keep entire ecosystems alive. The reason it works is that the ocean is vast, and the surface produces a lot of biological material. Even if only a small fraction of that material reaches the deep sea floor, it adds up over time. But the trench is so deep that marine snow has a long journey to make. As it falls, it gets eaten along the way. The deep ocean is not empty water with a clean, straight path from surface to bottom. It's full of organisms at different depths. Many of them feed on sinking particles. They intercept marine snow like a slow-moving delivery system. So by the time organic material reaches the bottom of the Mariana Trench, it's often reduced. Smaller, more processed, less energy-rich. That means the trench floor is living on the leftovers of the leftovers, which is one of the reasons trench ecosystems are shaped so strongly by scarcity. And scarcity changes everything. On the surface, if you're a predator, you can hunt frequently. Prey is often abundant. If you miss a meal, you can try again soon. In the trench, missing a meal might mean waiting a long time for the next opportunity. So deep sea food webs are built around a few key strategies: slow living, opportunism, scavenging, energy efficiency, and the ability to exploit food sources that would be ignored in more comfortable environments. One of the most important groups in deep-sea food webs is the microbial community. Bacteria and archaea in deep sediments break down organic matter. They process marine snow that settles onto the seafloor. They recycle nutrients. They produce chemical compounds that other organisms can use. In many ecosystems, microbes are treated as an afterthought because they're invisible. In the trench, microbes are the foundation. They are the engines that make the system run. If you imagine the trench floor as a place where dead organic material slowly accumulates, microbes are the ones turning that accumulation into usable energy pathways. Some animals feed directly on microbial mats or on sediment rich in microbial life. Others feed on those animals. The chain builds upward. Now, marine snow is the main supply line, but it's not the only one. There are also occasional larger food deliveries, and this is where deep-sea food webs get dramatic. Sometimes something big dies in the surface ocean and sinks. A large fish, a squid, a whale. This is called a food fall, and in the case of whales, it's called a whale fall. A whale fall is one of the most intense events the deep seafloor can experience. It's like a massive meal appearing out of nowhere, a sudden burst of energy in a world that is usually starved. When a whale carcass hits the seafloor, it can support a whole community of scavengers and specialized organisms for years. First come the large scavengers, like sharks and hagfish in shallower deep environments. Then smaller scavengers and worms. Over time, bacteria break down the remaining tissue and even the bones, releasing chemicals that support chemosynthetic communities. It becomes a temporary oasis of food. Now, whales don't sink into the deepest parts of the Mariana Trench in the way they might sink into other deep areas, and the trench floor is not constantly littered with whale carcasses. These events are rare, but the principle still matters. Big food falls happen, and when they do, they shape the deep ecosystem. Because deep-sea animals are adapted to take advantage of rare opportunities. That's why you often see scavengers like amphipods arriving quickly at baited cameras. They are tuned to detect food from far away. In a world where meals are unpredictable, you can't afford to ignore the scent of something edible. Amphipods are one of the key scavengers in trench environments. They're crustaceans related to shrimp, and some trench amphipods are large compared to shallow water relatives. They have bodies designed to handle pressure and to move across the seafloor. When a food source appears, amphipods can swarm it. Not in a chaotic frenzy like piranhas, but in a steady, efficient gathering. They feed, they tear, they carry away fragments. They make sure very little goes to waste. That behaviour is not just gross, it's essential. In the trench, waste is rare. Everything gets used. Another group that plays a major role is the deposit feeders. These are animals that consume sediment and extract organic material from it. Sea cucumbers are famous deposit feeders in many deep environments. They move slowly across the bottom, swallowing sediment, digesting what they can, and leaving behind processed material. It sounds simple, but it's one of the most reliable strategies in a place where food arrives in small amounts. If you can eat the ground itself and extract the tiny organic bits inside, you have a steady source of nutrition. Worms do this too. Many polychaete worms burrow through sediments, feeding on organic matter and microbes. Some worms are predators, some are scavengers, some are generalists, but many are part of the system that keeps energy moving through the trench floor. Now, at this point, you might be wondering something. If the trench relies on marine snow and occasional food falls, and if those are limited, then doesn't that mean the trench is basically a low-energy desert? Yes, in many ways it is, but deserts can still have life. The difference is that trench life is built around efficiency. One of the biggest misconceptions people have about deep-sea ecosystems is that they're always filled with monsters hunting each other in constant darkness. That image is popular because it's exciting, but in reality much of the deep ocean is quiet. The animals are spread out. Encounters are rare. Movement is slow. Many creatures live on the edge of hunger. Predators exist, but they often have strategies that reflect the environment. Some are ambush predators. They wait. They conserve energy. They strike when prey comes close. Some are opportunistic. They will hunt if they can, but they will scavenge if they must. Some are specialised for capturing prey that drifts past, like gelatinous organisms that trap small animals in tentacles. The deep sea is not a constant battle, it's more like a long test of patience. Now, we should talk about the mid-water zone, because the trench isn't just the bottom. The trench is a vertical world. Between the surface and the seafloor is a massive column of water, and that column is full of life. Some of the most important deep-sea food web activity happens in the midwater, not on the bottom. In the mesopelagic zone, sometimes called the twilight zone, there is a daily migration that might be the largest movement of animals on Earth. Every night, huge numbers of small organisms like lanternfish and zooplankton rise toward the surface to feed. Every day, they descend back into deeper water to avoid predators. This is called diel vertical migration. It's like the ocean breathing, and it matters because it moves energy. These organisms feed near the surface and then carry that energy downward in their bodies. When they excrete waste, when they die, when they are eaten, that energy becomes part of the deep system. So the deep sea isn't only dependent on passive sinking particles, it also receives energy through active movement. Now, the Mariana Trench is deeper than the zones where most of this migration occurs, but the principle still applies. The ocean is connected vertically. Energy flows downward in multiple ways. Another way energy reaches the deep is through sinking carcasses of mid-water animals. Not just surface animals. Fish die at depth. Squid die at depth. Organisms living in the deep water column contribute to the food supply of the seafloor, so the trench is part of a larger deep ocean economy. And like any economy, it has supply lines, bottlenecks and shortages. One of the most interesting aspects of deep-sea food webs is how much recycling happens. On land, you might see a dead animal and think of it as one event. Something dies, decomposers break it down, and nutrients return to the soil. In the deep ocean, decomposition is slower because of cold temperatures, but scavenging can be intense. Microbes break down material, invertebrates feed, predators feed on those invertebrates. The same energy can pass through many mouths. This is one reason deep-sea ecosystems can persist even with low energy input. They are good at using what they get. Now, there's another source of energy that can exist in deep ocean environments, and it's one that feels especially relevant to the idea of prehistoric life. Chemosynthesis. Chemosynthesis is the process where organisms produce energy by using chemical reactions rather than sunlight. In hydrothermal vents, microbes use chemicals like hydrogen sulfide released from the Earth's crust. In cold seeps, microbes may use methane. These microbes form the base of ecosystems that can thrive without sunlight. Hydrothermal vent communities are some of the most famous examples of life without light. They include giant tube worms, clams, crabs, and other creatures living around the vent chemistry. Now, the Mariana Trench is not known as a classic hydrothermal vent hotspot in the way some mid-ocean ridges are, but subduction zones can have chemical seeps and unusual geochemistry. Even without dramatic vents, there can be areas where chemistry provides additional energy pathways. And even if chemosynthesis is not the dominant system across the trench, the concept is important because it proves something. Life does not require sunlight, it requires energy. Sunlight is one source, but not the only one. This matters when we talk about prehistoric creatures because early life on Earth likely relied on chemical energy long before complex sunlight-based ecosystems dominated the planet. The deep ocean, with its chemical environments, can resemble those ancient conditions, so the trench is not just a place where old lineages might survive. It's a place where the basic energy logic of life can take forms that feel older. Now let's bring this back to the question of hidden creatures. A food web shapes what kinds of animals can exist. If energy is limited, you don't get endless large predators. You get fewer large animals, more small ones, more scavengers, more organisms adapted to low energy. That means if there are unknown prehistoric creatures hiding in or around the Mariana Trench, they are likely to fit one of a few categories. They might be scavengers that arrive quickly at food sources and then disappear. They might be deposit feeders that blend into the seafloor and are hard to notice. They might be predators that are rare and widely spaced, living in low numbers. They might be gelatinous or soft-bodied animals that don't leave obvious remains. They might be animals that live in the mid-water column rather than on the bottom, feeding on drifting prey. And they might be organisms that have evolved to exploit chemical energy in localized areas. Now, there's another layer to this, and it's something that makes deep-sea food webs feel eerie. The deep ocean is connected to death. That sounds dramatic, but it's simply true. Much of the energy that reaches the deep comes from dead material, dead plankton, dead fish, dead whales, waste, decay. Life down there is built on what falls from above. It's a world where death is not an interruption. It's the supply chain, and that can feel prehistoric because it reminds us of how life works at its most basic level. Life consumes life. Energy moves through bodies. Nothing is wasted. In the trench, that cycle is stripped down and made obvious. You don't have fields of grass. You have sediment with organic particles. You don't have forests. You have drifting debris. You don't have sunlight. You have chemistry and patience. Now, if you've ever wondered why deep-sea animals can look so intense, why they have large mouths and sharp teeth and strange hunting methods. Part of the reason is that in a low-energy world, you can't afford to miss an opportunity. If prey comes by, you have to take it. That's why some deep fish have expandable stomachs. They can swallow large prey because they don't know when the next meal will come. That's why some have teeth that curve inward, preventing prey from escaping. That's why some have lures or lights to attract prey in darkness. These aren't monsters, they're animals built for a harsh economy. Now, let's make one more important point. Deep-sea food webs are not uniform. They vary by region. They vary by depth. They vary by how much organic material sinks from above. They vary by currents, by seafloor shape, by proximity to productive surface waters. The Mariana Trench is in a region of the Pacific, and the productivity of surface waters above can influence how much food reaches the trench. Trenches can also act like traps, collecting sinking material in their deepest parts. This means the trench can be richer in organic material than a flat abyssal plain at the same depth, simply because of its shape. It can accumulate what sinks. That makes it more hospitable than you might expect given its depth. And that hospitability is part of why life can exist there. So the deep sea doesn't need sunlight, it needs supply, it needs recycling, it needs organisms that can make the most of scarce resources. And when you put all of that together, you get a food web that is quiet, efficient, and surprisingly robust. Now, with that foundation, we're ready to talk about the animals we've actually found in the trench. Not the imagined ones, not the rumoured ones, the real ones. Because once you see what is already living down there, the question changes. It becomes less about whether the trench can support life, and more about how much life it can hide from us. When you hear Mariana Trench, it's almost impossible not to picture something enormous, something with teeth, something with a silhouette that appears for half a second in murky water before vanishing. The trench has that reputation. It's the deepest place on Earth, so our brains treat it like the final level of the ocean, the place where the strangest things must be waiting. But the real creatures we've actually found down there are not always what people expect. They're often smaller, quieter, more practical, less like movie monsters and more like specialists. Animals that have adapted to pressure, cold and scarcity so completely that their bodies look like they were designed for a world made of darkness and weight. And once you start learning what they are, you realise something important. The trench doesn't need imaginary creatures to be unsettling. Reality is already weird enough. The first thing to understand is that the Mariana Trench isn't a single uniform habitat. It's a deep trench system with slopes, ridges, sediment plains, and microhabitats. The creatures found there are not all living at the absolute deepest point. Some live on the trench slopes, some live in the Hadal zone proper, some move between depths, some appear only in certain regions. So when we talk about trench creatures, we're talking about a range of organisms adapted to extreme deep-sea conditions, often found in depth beyond 6,000 metres. And the deeper you go, the more specialised the community becomes. Now, one of the most frequently encountered animals in the deepest trench environments is not a giant predator, it's an amphipod. Amphipods are small crustaceans related to shrimp and crabs, and they are some of the most successful scavengers in the deep sea. In the trench, amphipods often show up quickly when a baited camera or lander hits the bottom. They swarm the bait, they tear at it, they feed with an efficiency that feels almost mechanical, and they do it because the trench is a place where food is rare. If something edible appears, you don't hesitate. Trench amphipods can look different from shallow water amphipods. Some are larger, some have thicker bodies, some have longer appendages. Many are adapted to the pressure and cold. They don't have the sleek look of a surface shrimp. They look like they belong to the deep. And amphipods are important for another reason. They are part of the trench's cleanup crew. In the deep sea, nothing is wasted. Dead animals that sink become resources. Amphipods help break down that material, turning it into smaller pieces and making it available to other organisms. They are part of the recycling system that keeps energy flowing. They're not glamorous, but they're essential. If you've ever seen footage from a deep-sea baited camera, you might notice how quickly amphipods appear. It can be eerie. One moment the bottom looks empty. The next, it's covered in moving bodies. That sudden appearance is one of the reasons the trench feels alive in a way that surprises people. It isn't crowded all the time. It's more like a quiet room where something wakes up the moment you drop food into it. Another common group of trench residents is the polychaete worms. Polychaetes are segmented worms, often with bristles, and they exist in many marine environments. In the deep sea, they can be found burrowing in sediment, crawling across the bottom, or feeding on organic material. Some polychaetes are deposit feeders. They ingest sediment and extract nutrients. Others are scavengers. Others are predators that hunt smaller organisms. In trench environments, polychaetes can be part of the benthic community, living in or on the seafloor sediment. They may not be the most visually dramatic animals, but they are part of the foundation of the ecosystem. Worms are often underestimated because they don't look like what people imagine when they think of deep-sea mystery. But worms are ancient. They represent one of the basic body plans that has worked for a long time. Segmented, flexible, able to burrow, able to feed on organic matter. If you want to talk about prehistoric feeling life, worms are a good reminder that some of the oldest successful strategies are also the simplest. Then there are sea cucumbers. Sea cucumbers are echinoderms, related to starfish and sea urchins, and they are some of the most common animals on the deep sea floor in many regions. In the trench, certain types of sea cucumbers can thrive as deposit feeders, slowly moving across the sediment and processing it. Some deep-sea sea cucumbers look strange compared to the ones people see in shallow waters. They can be translucent. They can have unusual shapes. Some have appendages that help them move or feed. Some look like soft blobs drifting just above the bottom. They are not fast. They are not aggressive. But they are perfectly designed for a world where the main food source is organic material mixed into sediment. And again, their role is recycling. They keep the seafloor from becoming a dead layer of unused debris. They process it. They move nutrients through their bodies. They contribute to the flow of energy. Now, if you're hoping for fish, the trench does have fish. But the fish of the Hadal zone are not what most people picture. The most famous trench fish is the snailfish. Snailfish are part of a family of fish that often have soft bodies and a gelatinous appearance. They are not sleek predators like sharks. They are not muscular swimmers like tuna. They are built for the deep. Trench snailfish have been observed at depths that are astonishing. Some have been recorded in the Hadal zone at depths over 8,000 meters. They are among the deepest living fish ever documented, and their existence tells us something important. Fish, which are vertebrates with complex physiology, can adapt to extreme depth. They can solve the pressure problem. They can function in cold darkness, but they do it with specialized chemistry, specialized membranes and bodies that are not built like shallow fish. Trench snailfish often appear pale or translucent. Their bodies look soft. Their heads can look large relative to their bodies. They can appear almost delicate. But they are not delicate. They are living proof that vertebrate life can exist in one of the harshest environments on Earth. Snailfish feed on small crustaceans and other invertebrates. They are predators, but in the trench, predation is not always about speed. It's often about opportunity. If you can locate prey and capture it, you survive. And snailfish are adapted to do exactly that. Now, here's a detail that makes trench fish even more interesting. There may be depth limits for fish. Scientists have suggested that beyond certain depths, the chemistry required for fish to maintain protein stability becomes difficult. The TMAO levels needed may become too high. Osmotic balance may become unsustainable. This could create a natural boundary beyond which fish cannot live. That would mean the deepest parts of the trench are dominated by invertebrates, not fish. And that's exactly what some observations suggest. So the trench is not just a deep place with fish. It's a deep place where fish exist up to a point, and then the ecosystem shifts. That shift is important because it tells us the trench is not a simple extension of the surface. It's a gradient of biological possibility. Now, beyond these more familiar groups, there are other creatures found in deep trench environments that deserve attention. One is the isopod. Isopods are crustaceans related to pillbugs and woodlice, but in the ocean they can take on very different forms. Some deep-sea isopods can be large, with armoured bodies and a slow, deliberate movement. They look like ancient scavengers, like something built to crawl through darkness and wait for food. Not all isopods live in the deepest trench, but deep-sea isopods are part of the broader deep ecosystem, and they represent the kind of body plan that thrives in low-energy environments. Armoured, efficient, opportunistic. Another group is the Xenophyophores. These are large, single-celled organisms, which is already strange. They are not animals. They are giant protists that build structures on the seafloor, often using sediment and particles. They can form complex shapes and create habitats for smaller organisms. The idea that a single-celled organism can be large enough to be seen and to form structures on the seafloor is one of those facts that quietly rearranges your sense of what life looks like. Xenophyophores have been found in deep-sea environments, including trenches. They may play roles in sediment ecosystems and provide microhabitats for other creatures. They are not predators. They are not dramatic. But they are a reminder that the deep sea is full of life forms that don't fit our surface categories. Then there are foraminifera and other deep-sea microbes. If you take sediment samples from the trench, you find microbial communities adapted to high pressure, bacteria and archaea that process organic material. These microbes are not just background, they are the foundation. Some are piezophiles, meaning they thrive under pressure, and microbes can shape the entire ecosystem. They determine how organic material is broken down. They influence nutrient availability. They create chemical gradients. In a way, trench ecosystems are microbial ecosystems with larger animals built on top. Now, when people talk about creatures we've found in the trench, they sometimes focus on the most visually striking footage. The fish, the amphipods, the strange shapes on the sea floor. But a huge part of what we know comes from samples, not videos. Scientists collect sediment cores. They analyse DNA. They identify species by genetic markers. They study chemical composition. They look at how organisms are related. This is where things get even more interesting. Because genetic studies suggest that trench environments can host unique species adapted specifically to Hadal life. These species are not simply shallow animals that wander down. They are specialised trench dwellers, and in some cases they are found only in certain trenches, suggesting isolation and unique evolutionary pathways. This is where the trench starts to feel like a set of separate worlds. Different trenches around the globe can host different Hadal communities. The Mariana Trench is one, the Tonga Trench is another, the Japan Trench, the Kuril-Kamchatka Trench. Each one can have unique features and unique life. That means the Mariana Trench is not just the deepest place. It's one of multiple deep frontiers, each with its own ecosystem. And because these ecosystems are isolated, they can become laboratories for evolution. Now, let's talk about what trench creatures often have in common, because this is where the prehistoric feeling starts to show up again. Many trench animals have adaptations that make them look unfamiliar. They may be pale, because pigmentation is less useful in darkness. They may have reduced eyes, because seeing is less important. They may have enhanced sensory structures, because detecting vibrations and chemicals matters more. They may have soft bodies, because rigid structures can be a disadvantage under pressure. They may have slow movement, because energy is precious. They may have wide mouths or expandable stomachs, because meals are unpredictable. They may have long lifespans because growth and reproduction can be slow. These traits combine into creatures that look like they belong to a different era, and yet they are modern. They are alive now. They are part of the current world. That's one of the most unsettling truths about the trench. It's not a fossil record, it's a living system. Now, there is another category of trench discovery that doesn't get as much attention as look at this weird fish, but it matters for our topic. we have found evidence of human pollution in trench animals. Microplastics have been detected. Persistent organic pollutants have been found. Chemical contaminants can accumulate even in deep organisms. This means trench creatures are not isolated from human activity as much as we might like to believe. The trench is far away, but it is connected to the surface through the ocean's circulation and through sinking debris. That doesn't change the mystery of trench life, but it adds a layer of reality. The trench is not a fantasy realm. It's part of the same planet we live on, and it is affected by what we do. Now, with all these creatures in mind, amphipods, worms, sea cucumbers, snailfish, microbes, protists, we can ask a more specific question. If this is what we've found, what might we have missed? Because the creatures we have actually documented are only the ones we've been able to observe or collect. And as we've already discussed, trench exploration is limited. There are huge gaps in our knowledge. We haven't filmed every part of the trench. We haven't sampled every slope. We haven't studied every season. We haven't observed long-term behaviours. We often see creatures only when they come to bait. That means our picture of trench life is incomplete. Some animals may avoid bait, some may avoid light, some may be rare, some may live in microhabitats that are hard to reach, some may be fragile and break apart when collected. And that leads us directly into one of the most interesting categories for hidden prehistoric creatures: living fossils. Not in the exaggerated sense of a dinosaur hiding under the seafloor, but in the real biological sense of lineages that have survived with recognizable traits from ancient eras. Because if the trench can support specialized animals, and if it can hide them from us, then it can potentially shelter lineages that feel like they belong to deep time. So next, we're going to look at that idea more closely. The animals that seem to carry ancient history in their bodies, and why the deep ocean is one of the best places on Earth for those lineages to persist. There's a particular kind of thrill that comes from seeing something alive that you thought belonged only in stone. Not in a dramatic jump scare way, but in a quieter way that makes your brain pause for a second and go, wait, that's still here? Because most of us grow up with the idea that the past is finished. The dinosaurs are gone. Ancient oceans are gone. The creatures that once ruled the planet have been packed away into museums and textbooks and fossil displays under glass. But every so often, nature does something that feels like it's breaking the agreement. A creature shows up that looks like it's stepped out of a different era. It moves like it has all the time in the world. Its body plan looks older than the idea of a city. And suddenly the line between prehistoric and modern gets blurry. These are the animals we often call living fossils. It's a phrase people love because it's simple and it sounds dramatic, but it's also a phrase that can be misunderstood, so let's be careful with it. A living fossil does not mean an animal that has stayed unchanged for hundreds of millions of years. Evolution doesn't stop. Populations shift. Genetics change. Adaptations accumulate. Even if an animal looks similar to its ancient relatives, it has still been evolving the entire time. What the phrase really points to is something more specific, a lineage that has retained a recognizable body plan over an extremely long period, a design that still works, a blueprint that nature never had to fully replace. And the deep ocean, especially deep and stable environments, is one of the best places on Earth for those blueprints to persist. Because when the environment stays relatively consistent, the pressure to change in dramatic ways can be lower. If a body plan works in cold darkness and high pressure, it can keep working for a very long time. That's one reason the deep sea feels prehistoric. It's not just because it's dark, it's because it can act like a refuge for ancient strategies. Now, if we're talking about living fossils, the most famous example in the modern imagination is probably the coelacanth. The coelacanth is a large, lobed-finned fish with thick fins that look almost like limbs. It belongs to a group of fish that were thought to have gone extinct around 66 million years ago, the same general era when dinosaurs vanished. For decades, it existed only as fossils. Then, in 1938, one was caught off the coast of South Africa, alive, real, not a mistake. That moment was a shock to science and a gift to every person who loves the idea that the ocean still holds secrets. The coelacanth doesn't live in the Mariana Trench. It lives in deep waters, but not trench depth. Still, it matters because it proves a point. It proves that ancient lineages can survive unnoticed, not because they're hiding in a magical way, but because the ocean is huge and human observation is limited. And if a creature can survive for tens of millions of years in deep water without us noticing, it forces you to rethink what else might be out there. Another group that feels ancient is sharks. Sharks have been around for hundreds of millions of years. They existed long before dinosaurs. They survived mass extinctions that wiped out countless other lineages. They have remained successful because their basic design is brutally effective. A streamlined predator with replaceable teeth, powerful senses, and a body built for movement through water. Now, sharks are not trench residents in the deepest Hadal zones, but deep-sea sharks exist. Some live in cold, dark waters and have traits that feel ancient. The frilled shark is one of the best examples. The frilled shark looks like something drawn by someone who had heard rumours about sharks but had never seen one. It has a long eel-like body. It has a wide mouth with rows of needle-like teeth. It has gill slits that give it a strange, ruffled appearance. It lives deep, often hundreds to over 1,000 metres down. It is not a trench creature in the Challenger deep sense, but it's part of the deep ocean world that surrounds trenches, and it carries that prehistoric look so strongly that people sometimes call it a living fossil. It's a reminder that ancient-feeling predators are not imaginary. They exist. Then there's the Greenland shark. This one doesn't look like a movie monster. It looks like a slow, heavy shark that seems half asleep. But what makes it extraordinary is its lifespan. Greenland sharks are believed to live for centuries. Some estimates suggest they can live 300 to 500 years. That means there could be Greenland sharks alive today that were born before entire nations existed in their current form. They live in cold, deep waters, often in the North Atlantic and Arctic regions, not in the Mariana Trench. But again, they show the same pattern. Deep and cold environments can support long-lived animals. Slow metabolism, slow growth, slow aging. That kind of life history feels prehistoric because it operates on a different timeline than our own. It's the difference between an animal that lives 5 years and an animal that might outlive your entire family tree. And sharks are only one part of the story. If you want to find living fossils, you also look at animals that are less flashy but more ancient in their body plans. Take the horseshoe crab. Horseshoe crabs are often called living fossils because their body plan resembles ancient relatives from hundreds of millions of years ago. They look like armoured creatures from a time when the ocean was full of strange arthropods. They live in shallow coastal waters, not the deep sea, but their existence is still relevant because it shows how some body plans can persist for extraordinary spans of time. Arthropods in general are ancient. The basic concept of a segmented body with an exoskeleton and jointed limbs has been successful for a long time. In the deep sea, crustaceans like amphipods and isopods are part of that ancient arthropod story. When you see an isopod crawling on the deep sea floor, it can feel like you're watching an ancient design doing what it has always done. Then there are the nautiluses. Nautiluses are cephalopods, relatives of squid and octopus, but unlike their shell-less cousins, nautiluses carry a spiral shell. They float using chambers filled with gas, adjusting buoyancy by controlling the fluid inside. Their shells resemble fossils of ancient ammonites and other shelled cephalopods that once filled prehistoric oceans. Nautiluses are not trench animals, and their depth range is limited compared to trench depths, but they are another example of a lineage that retains an ancient-feeling design. And cephalopods themselves are an old story. Squid and octopus are modern in many ways, but their lineage stretches back deep into evolutionary history. Now, if we shift from the famous examples to the creatures more directly connected to the trench, the living fossil idea becomes more subtle. Because trench life is not full of coelacanths and nautiluses, it's full of specialised organisms that don't always have popular names. Many of them are small, many are rarely seen, many don't have fossil records that are easy to connect to the present. but the trench can still preserve ancient-feeling traits. One example is the way many trench animals rely on scavenging and deposit feeding. Scavenging is an ancient strategy. It doesn't require complex hunting tactics. It requires detection, movement, and the ability to break down food. In the early oceans, before complex ecosystems developed, scavenging would have been a reliable way to survive. Even today, it remains essential. Deposit feeding, consuming sediment, and extracting organic material is another ancient strategy. It's a way of living that can persist in stable environments where organic matter accumulates. These strategies can make trench ecosystems feel older because they are built on basic energy flows rather than lush surface abundance. Then there are the microbial communities. Microbes are the oldest form of life on Earth. They dominated the planet long before complex animals existed. In the deep ocean, microbes remain central. They are not just background life, they are the base of the ecosystem. Some microbes in the deep are adapted to high pressure and low temperature. They thrive in conditions that resemble parts of early Earth. They carry metabolic pathways that are ancient in the evolutionary sense. So when you look at the trench, you're not just looking at strange animals. You're looking at microbial life doing what microbes have always done: processing energy, recycling matter, surviving in extremes. That alone is prehistoric in the truest sense. Now there's another reason trench animals can look like living fossils, and it has to do with body structure. In the deep, many animals have reduced skeletons, reduced pigmentation, reduced eyes, and soft bodies. To a surface human, those traits can look primitive. They can look like an early stage of evolution. But that's not necessarily what they are. They are not less evolved. They are differently evolved. Reduction is not backwardness, it's efficiency. If eyes aren't useful, reducing them saves energy. If pigments aren't useful, losing them saves resources. If heavy bones aren't useful, minimizing them helps. So the trench can produce animals that look stripped down, as if evolution went back to basics. That creates a prehistoric impression, even when the animal is fully modern. This is important because it means the trench can generate prehistoric-looking life, even without preserving truly ancient lineages. It can make modern animals look ancient, but it can also preserve lineages that really are old, and the deep ocean has a track record of doing that. Now, let's talk about one of the most interesting categories in the living fossil discussion: animals that survive in deep refuges while their relatives vanish from shallower environments. This is one of the most plausible ways an ancient lineage can persist. When surface environments change rapidly, many species go extinct. But if a population lives deeper, where conditions are more stable, it may survive. Over time, that deep population becomes isolated. It may evolve into a distinct species, but it may retain traits that resemble its ancient ancestors. This is a refuge model. The deep ocean becomes a shelter during turbulent times. Mass extinctions, climate shifts, ocean chemistry changes, all of these can wipe out shallow ecosystems. But deep environments can be buffered. Not safe, but less chaotic. So the deep sea can act like a biological archive. Not a perfect archive, but a place where certain lineages can persist when the surface world is reset. Now, this connects directly to the Mariana Trench. The trench is one of the most stable environments in terms of temperature and light. It is cold and dark all the time. That stability can make it a refuge for organisms adapted to those conditions. If a lineage can tolerate pressure, it can potentially persist for a long time in the trench. And because the trench is isolated, those lineages can remain unknown. Now here's where the prehistoric creature hiding in the trench idea starts to sharpen. If we want to imagine a creature that still exists down there, something that feels like ancient history, it doesn't need to be a dinosaur. It doesn't need to be enormous. It doesn't need to be something we've seen in movies. It could be a deep-sea lineage that has survived with ancient traits. It could be an animal with a body plan that resembles early forms. It could be a creature that lives in low numbers, in a stable environment, feeding on scarce resources, avoiding disturbance. It could be something that we've never documented because we haven't spent enough time watching, And there's another important point. The trench is not just deep, it's difficult to explore. Our methods of exploration often bias what we find. We use baited cameras, so we see scavengers. We use nets and traps, so we catch what can be caught. We use submersibles, but we only cover small areas. That means we may be missing animals that don't respond to bait, don't get trapped easily, or live in places we haven't sampled. So even if the trench doesn't contain unknown giants, it could contain unknown lineages. And those lineages could feel prehistoric because they carry traits that connect them to deep evolutionary history. Now, let's also address a small but important reality. Sometimes, the deep ocean feels prehistoric because it contains animals that resemble fossils we've seen. But fossils are incomplete. We often find hard parts, shells, bones, teeth. Soft-bodied animals rarely fossilize well. That means our picture of prehistoric life is biased toward creatures with hard structures. We imagine ancient oceans full of armoured creatures and skeletons because those are what preserve. But ancient oceans were also full of soft-bodied life. Jelly-like organisms, worms, larvae, gelatinous predators, things that left a little trace. And the deep ocean today contains a lot of soft-bodied life that is hard to observe and hard to preserve. So the trench could contain organisms that resemble ancient soft-bodied life, and we would have a hard time proving it. Because they might not leave bones, they might not leave shells, they might simply exist, feed, reproduce and disappear. That kind of life is easy to miss. Now, with living fossils in mind, the next step is to look at something that sits right on the edge between fact and speculation. Reports of giant shadows. Not the kind of reports that come from reliable data sets, but the kind that keep showing up anyway. The kind that make people wonder if the deep sea sometimes produces animals larger than we expect, or at least larger than we have documented. Because even if the trench itself is not a perfect home for giant predators, the deep ocean surrounding it might still hold surprises. And the idea of something large moving through darkness is one of the oldest deep-sea fears humans have ever carried. So next, we're going to talk about why deep-sea monsters keep getting reported, what those reports might really mean, and how the ocean's size and darkness can turn ordinary biology into something that feels prehistoric. There's a pattern that shows up again and again whenever humans talk about the deep ocean. Someone sees something they can't explain. A shape passes through the water, too large to feel comfortable, too fast to identify, too strange to categorize in the moment. A shadow crosses a camera frame and the footage ends before anyone can pause it properly. A sonar return suggests something big, then disappears. A fishing line goes tight, then snaps, as if something far heavier than expected grabbed it and decided it didn't like being interrupted. And almost immediately the same thought rises in the human mind. What was that? Because the ocean is the perfect place for that question to live. It is vast, it is dark, it is layered, it is difficult to observe, it is filled with animals that already look strange, and most importantly it has enough empty space for your imagination to stretch out and get comfortable. So when people say deep-sea monsters keep getting reported, it's not just because people enjoy telling stories. It's because the deep ocean produces conditions where misinterpretation is easy, and where real surprises are possible. And those two things, misunderstanding and possibility, create the perfect breeding ground for giant shadows. Now, let's be clear about what we mean by monster. In this context, it usually means a creature that feels too large, too old, or too unfamiliar to fit into what people think should exist. Sometimes it's imagined as a prehistoric survivor. Sometimes it's imagined as an undiscovered species. Sometimes it's just described as something huge. But the deep ocean doesn't need fantasy to create that feeling. It can do it with ordinary animals, ordinary physics, and a little bit of human psychology. Because the deep ocean is an environment where you rarely get a clear view. On land, if you see an animal, you usually see it in good light. You see its outline, you see its movement, you see how big it is relative to trees, rocks, or buildings. Even if you're surprised, you have reference points. Underwater, especially in deep water, reference points disappear. A fish passing in front of a camera can look enormous if the camera has no nearby objects for scale. A creature close to the lens can look bigger than it is. A creature far away can look smaller, but still unsettling because its shape is unclear. Water distorts, light bends, visibility is limited, particles float through the frame. The camera itself may be shaking slightly. The scene may be illuminated only by a small artificial light, which creates harsh shadows and deep black backgrounds. This is how giant shadows are born. A normal animal becomes a mystery because you can't see enough of it. And when you can't see enough, your brain fills in the missing parts. This is not a weakness. It's a survival tool. Humans evolved to detect threats quickly. If something moves in the dark, it's safer to assume it might be dangerous. If you see a large shape and can't identify it, your brain doesn't calmly wait for more data. It reacts, it labels it as unknown, and unknown often feels threatening. So the deep ocean taps into something old in us. Not just curiosity, but caution. Now, the ocean also has a long history of producing stories that sound unbelievable until they aren't. Giant squid were once considered myths. Sailors told stories about enormous tentacles pulling ships down, and for a long time people dismissed it as exaggeration. Then bodies washed ashore, then specimens were collected, then cameras finally captured footage of giant squid alive in the deep. The stories were exaggerated, but the core truth was real. There are squid in the deep that are huge. There are also colossal squid, even larger, with massive eyes and thick arms. These animals exist, and they live in deep waters where humans rarely see them. So when someone says they saw a giant shape in the deep, it's not automatically nonsense. The deep ocean has already proven that large, strange animals can exist beyond our regular observation. Now let's talk about the kinds of evidence that tend to fuel monster reports. One category is visual footage. Deep-sea cameras, especially those used in exploration or research, sometimes capture fleeting shapes. A large body passes through, a tail flicks, a shadow moves across the light, a long form drifts out of frame. The problem is that deep-sea footage is often limited. Cameras may be stationary, lighting may be narrow, the field of view may be small, and animals may not linger. So you end up with clips that show movement without context. That's enough to spark speculation. Another category is sonar. Sonar is one of the most powerful tools humans have for detecting objects underwater, but it has limitations. Sonar can show you that something is there. It can show you size and movement patterns, but it doesn't always tell you what the object is. A large school of fish can appear as a single large mass. A group of animals moving together can look like one giant thing. Layers of water with different temperatures can create false echoes. Noise can distort readings. And in the deep ocean, sonar data can be hard to interpret without direct observation. So sometimes a sonar monster is simply a school of fish. Sometimes it's a whale at depth. Sometimes it's a submarine or a geological feature, and sometimes it's something unknown. The third category is fishing encounters. People have been pulling things out of the ocean for as long as humans have had hooks and nets. Fishermen have stories about lines snapping, nets tearing, and something huge dragging equipment away. Some of those stories are exaggerations, some are misinterpretations, but some are real encounters with large animals. A big shark can destroy a net. A sperm whale can become entangled. A giant squid can grab bait. Even a large fish can feel enormous when you're on the other end of a line and you can't see it. So fishing stories are messy evidence. They're emotional. They're often told after the fact. But they still contribute to the sense that the ocean holds things bigger than we expect. Now, why do these reports feel especially connected to the Mariana Trench? Because the trench is the ultimate symbol of ocean depth. Even if a sighting happens far from the trench, people connect it to the trench in their minds because the trench represents the deepest place. It becomes the default home for anything unknown. It's like how people associate mysteries with the dark forest. Even if the event happened in a field, the symbol takes over. So the Mariana Trench becomes a narrative container for deep-sea monsters, whether or not the creatures actually live there. But there's another reason the trench and its surrounding deep waters are fertile ground for monster reports. We have not observed them continuously. We have not spent enough time there. We have not filmed the deep ocean in the way we film surface wildlife. We don't have long-term, wide-area surveillance of trench environments. So even if a large animal existed, the odds of us capturing it on camera are low. Think about how hard it is to film rare animals on land, like snow leopards, even with modern equipment. Now imagine trying to film a rare animal in complete darkness under crushing pressure across thousands of square kilometers of ocean, where your camera can only cover a tiny patch at a time. The deep ocean doesn't hide creatures by being clever, it hides them by being huge. Now let's talk about the biology of giant shadows, because size is one of the most misunderstood aspects of deep sea life. Many people assume the deep sea produces giants, and in some cases it does. There is a phenomenon called deep sea gigantism, where certain animals like some crustaceans and squid can grow larger than their shallow water relatives. But gigantism is not universal. The trench is not full of giant versions of everything. Size depends on energy availability, temperature, oxygen levels, and evolutionary history. In some deep environments, being large can be beneficial. A larger body can store energy, withstand starvation, and travel farther. It can also reduce predation risk in some cases. But in the trench, where food is limited, extreme size can be hard to sustain. A giant predator needs a steady supply of calories, and the trench does not provide that easily. So the trench is not the best place for a massive animal to live full time. However, the deep ocean around the trench, the slopes, the mid-water zones, and the broader deep sea environment can support larger animals. Giant squid, for example, live in deep waters, not necessarily in the deepest trench bottom, but in the deep ocean realm where pressure is high but not Hadal maximum. Large sharks can roam deep slopes. Sperm whales dive deep to hunt squid. So the deep ocean has large animals, and those animals can create giant shadows. A squid passing close to a camera could look like a monster. A large fish with a long body could look prehistoric. A shark moving through darkness could look like a moving submarine. And because the deep ocean is so hard to observe, these encounters remain ambiguous. Now, there's another factor that fuels monster reports, and it's the way deep sea animals behave around light. Many deep sea animals are attracted to light, while others avoid it. Some are curious, some are cautious, some are drawn in by the possibility of prey, because light can attract smaller organisms. So when we drop a camera with lights into the deep, we're not simply observing natural behaviour, we're introducing an artificial stimulus into an environment that rarely experiences it. That means what we see on camera might not represent normal behaviour. A creature might approach because it's curious, or because it associates light with food. Another might flee. Another might circle at the edge of visibility. This creates footage that feels eerie, because animals appear and disappear at the edge of the light cone. A shadow at the boundary can look larger than it is. A movement outside the light can look like something lurking. So the very act of observing can create the impression of monsters. Now, let's talk about something that doesn't get enough attention. The human tendency to underestimate the ocean's size and overestimate how much we've seen. We live on a planet where the ocean covers more than 70% of the surface. Most of that ocean is deep. And the deep ocean is not just a little deeper than a swimming pool, it is kilometres deep across enormous areas. If you could drain the ocean and walk across the seafloor, you would be walking across a landscape larger than all the continents combined. You would see mountains, plains, ridges, trenches, and valleys that rival land features in scale. And we have not walked it. We have not mapped it in full detail. We have not observed its life the way we observe land wildlife. So when people say, surely we would have found it by now, the honest answer is no, not necessarily. We have found new species in relatively shallow waters. We have found new species in well-studied regions. We discover new deep-sea organisms regularly. Some are small, some are strange, some are completely unexpected. So the deep ocean can still hold surprises, but we also need to be realistic. The deep ocean is not hiding endless giant prehistoric reptiles. Large animals require energy, and the deep ocean's energy budget is limited. The deeper you go, the less energy is available. That's why trench ecosystems are often dominated by smaller organisms and scavengers. So the most likely explanation for many monster reports is not a single hidden giant species. It's a combination of factors: limited visibility, poor scale reference, misinterpretation of sonar, rare encounters with known large animals, the deep ocean's tendency to produce unusual body shapes, and human imagination filling gaps. But there is still a middle ground between fantasy and dismissal, a middle ground where some reports might reflect real unknowns. Because even if the trench itself is not a home for a giant predator, the deep ocean can still contain species we haven't documented. Large fish species, large squid, large gelatinous organisms, rare sharks, deep water animals that avoid cameras and nets. And if those animals are rare and wide-ranging, we might see them only as shadows. We might hear them only as sounds. We might detect them only as brief sonar returns. We might catch them only once in a century. So the deep ocean can produce monsters in two ways. Sometimes it produces a monster in our mind, because we can't see clearly. And sometimes it produces a monster in reality, because nature has had millions of years to evolve creatures in a world we barely visit. Now, if you want one of the most interesting examples of why deep-sea mystery persists, it comes down to a simple biological truth. Soft-bodied creatures are hard to prove. If a giant squid dies, it can be eaten quickly, or it can sink and decompose. If it washes ashore, we might find it. But if it dies in deep water and is consumed, it might leave little trace. If a large gelatinous organism dies, it might dissolve and vanish. If a creature lives deep and rarely approaches the surface, it might never be caught. So the deep ocean could contain large organisms that leave almost no evidence behind. That's not a guarantee. It's a possibility. And possibility is what keeps the reports alive. Now there's another aspect of giant shadows that matters, especially for our topic about prehistoric creatures. The deep ocean is full of animals that already look prehistoric. Even if they aren't ancient survivors, they look that way to us because of their teeth, their armour, their slow movement, their pale bodies, their strange proportions. So when someone sees a shadow, their brain doesn't interpret it as unknown fish. It interprets it as something ancient, because the deep sea already has that aesthetic, and once that aesthetic is in your mind, every unclear shape becomes part of the same story. Now, as we move forward, we're going to talk about creatures that are not just reported, but are real and documented, and still feel like they shouldn't exist. Soft-bodied organisms in the deep, jellies, siphonophores, creatures that leave no bones behind, because if there is any category of life that could hide in the Mariana Trench without us noticing, it's the kind of life that doesn't leave fossils, doesn't leave skeletons, and doesn't survive collection. It just exists. Quietly, in the dark, and if that doesn't sound like the perfect hiding strategy, it's hard to imagine what does. If you wanted to design a creature that could live in the deep ocean and remain almost impossible to prove, you wouldn't give it bones, you wouldn't give it a hard shell, you wouldn't give it teeth that could wash up on a beach, you wouldn't give it anything that lasts. You'd make it soft, you'd make it fragile, you'd make it mostly water, and you'd let it drift through darkness like a living thought, present for a moment and then gone. That's what a lot of deep-sea gelatinous life is like, and it's one of the best reasons the deep ocean can still feel full of unseen things. Not because the trench is hiding a dinosaur, but because it's likely hiding creatures that leave no trace when they die. When we talk about deep-sea mystery, we often focus on animals that look dramatic on camera. Fish with huge teeth, squid with long arms, sharks with strange faces, crustaceans swarming bait. But there's a whole other category of life in the deep that doesn't show up as easily. Life that doesn't get caught in nets. Life that doesn't survive being brought to the surface. Life that doesn't leave a skeleton behind. Jellies, siphonophores, ctenophores, salps. larval forms that look like ghosts. These organisms make up a huge portion of deep ocean biomass in some regions, and yet they are often missing from the public imagination because they are hard to study and even harder to display. If you've ever visited an aquarium, you might have seen jellyfish floating in a tank under soft blue light. They look delicate and calm. They pulse slowly like they're breathing. Now imagine that same kind of life, but adapted to deep darkness and high pressure, moving through water that is near freezing in a world where the only light comes from living bodies. That's the phantom jelly zone. Not a single location with a sign on it, but a category of life that can exist throughout the deep ocean, including in regions around trenches, and sometimes in the trenches themselves. And what makes it so interesting is that gelatinous life has a kind of invisibility built into it. First, gelatinous animals are often transparent. Transparency is one of the best forms of camouflage in the ocean. If you're clear, there's nothing to see. Light passes through you. Your outline disappears. In the deep ocean, where light is already scarce, transparency becomes even more effective. Second, gelatinous animals are fragile. A fish can be caught in a net and still be recognizable. A crab can be pulled up and still be intact. But a jelly-like organism can be destroyed by the turbulence of capture. It can tear, it can collapse, it can turn into unrecognizable tissue. So even if gelatinous animals are common, our sampling methods can miss them. Third, gelatinous animals don't fossilize well. Fossils tend to preserve hard parts: bones, shells, teeth, armoured plates. Soft tissue rarely leaves a lasting record. There are exceptions, but in general, gelatinous life disappears without leaving evidence. That means if a large gelatinous organism existed in the deep ocean and it died, it might leave nothing behind. No bones to find, no shell fragments, no clear remains, just organic material that gets consumed and recycled, and that makes gelatinous life one of the most plausible categories for hidden creatures. Not because it's supernatural, because it's hard to detect. Now, let's talk about what gelatinous animals actually are, because the word jellyfish gets used loosely. A jellyfish is typically a cnidarian, part of a group that includes corals and sea anemones. They have stinging cells called nematocysts, which they use to capture prey and defend themselves. But the deep ocean also contains ctenophores, often called comb jellies. These are not true jellyfish, they don't have stinging cells. They move using rows of tiny cilia that look like combs. In light, those comb rows can shimmer with rainbow colours. In the deep, a comb jelly can look like a floating piece of glass with a faint glow. Then there are salps, which are tunicates, closer to vertebrates than you might expect. Salps are barrel-shaped, gelatinous organisms that filter feed on plankton. They can form chains and drift through the water column. And then there are siphonophores. Siphonophores are some of the strangest animals in the ocean because they aren't exactly one animal in the way we usually mean it. They are colonies of specialized individuals called zooids, all genetically identical, working together as one functional organism. One part might handle movement, another part might handle feeding, another part might handle reproduction. Together they form a single creature-like system. The Portuguese man-o'-war is a famous siphonophore, and it lives at the surface. But deep-sea siphonophores can be far more bizarre and far larger. Some siphonophores can reach lengths of many meters. There are reports of siphonophores being tens of meters long, making them among the longest animals on Earth. They are not thick, muscular monsters. They are long, delicate chains of living tissue, drifting and feeding in the water column. And because they are so fragile, they are rarely seen intact. Now imagine one of these creatures drifting in the deep ocean near the trench. It wouldn't need to hide in a cave. It wouldn't need to avoid humans deliberately. It would simply exist in a place humans rarely look, and even if we did look, it might not show up clearly. A long, transparent siphonophore passing through a camera's light could look like a shadow, a ghostly ribbon, a shape that doesn't make sense. And if it died, it would leave almost nothing behind. That's why gelatinous life is such a powerful piece of the deep ocean mystery. Now, how do gelatinous animals survive in the deep? Their bodies are mostly water, which helps with pressure. A body that is largely water doesn't compress the way gas-filled structures do. Gelatinous tissue can tolerate pressure better than rigid structures in many cases. They also often have low-energy lifestyles. They drift, they pulse slowly, they capture prey that comes to them. This is a perfect strategy for a low-energy environment. Instead of chasing prey, you become a trap. You let the ocean bring food to you. Some jellies use tentacles to catch small fish and crustaceans. Some comb jellies capture prey with sticky cells. Some siphonophores have stinging tentacles that can paralyze prey. They can be efficient predators without needing speed. And because they are often transparent, they can be difficult for prey to see. That's another advantage. Now, one of the most important things to understand about gelatinous life is that it can be abundant even when it's hard to detect. There have been studies suggesting that gelatinous organisms are more common in the deep ocean than we once realized. Traditional sampling methods, like nets, can destroy them or miss them. But newer tools, like remotely operated vehicles with cameras, have revealed a surprising diversity of gelatinous life in deep water. That means our picture of the deep ocean has been incomplete for a long time. We thought it was dominated by fish and crustaceans because those are what we caught. But the deep is also full of delicate drifting predators and filter feeders that don't show up in nets. This is a reminder that deep ocean knowledge depends heavily on technology. As our tools improve, the deep becomes less empty and more crowded. Now, what does this mean for the Mariana Trench specifically? The trench itself is extremely deep, and the deepest parts may have fewer gelatinous animals than some mid-water zones because of energy constraints. But the trench is connected to the deep ocean around it. The slopes, the water column above, and the surrounding Hadal environment can all host gelatinous life. And even if gelatinous organisms are not the dominant residents of the trench floor, they can still be part of the trench ecosystem. Some gelatinous animals can sink when they die, becoming food for seafloor scavengers. Others may live at depth and feed on smaller mid-water organisms. So gelatinous life can be part of the energy flow into the trench. Now there's another reason gelatinous life feels like it belongs in a prehistoric story. It's ancient. Cnidarians, the group that includes jellyfish, are among the oldest animal lineages. They appear early in the history of multicellular life. Jellyfish-like forms have existed for hundreds of millions of years. So when you see a jellyfish, you're not just seeing a modern creature. You're seeing a body plan that has persisted for an enormous span of time. A drifting bell with tentacles is a design that works. It worked in ancient seas. It works now. And in the deep ocean, where conditions can be stable, it can continue to work. So gelatinous life is both ancient in lineage and mysterious in detection. It's the perfect combination for the prehistoric creature hiding in the deep idea. Not because it's a dinosaur, because it's a survivor. Now, there's a detail about gelatinous animals that often surprises people. They can be predators of surprisingly large prey. Some jellyfish can capture fish. Some siphonophores can trap small fish and crustaceans in their tentacles. Some deep-sea jellies have long trailing structures that act like fishing lines, increasing the area they can cover. And because the deep ocean is dark, prey may not see them until it's too late. So gelatinous animals can be more active in the ecosystem than their slow pulsing suggests. They are not just passive drifters, they are hunters in their own quiet way. Now, let's talk about why gelatinous life leaves no trace, because this is the core of the phantom jelly idea. If a fish dies, it may leave bones. Those bones can sink and remain for a while. Teeth can persist. Hard structures can be found. If a squid dies, its beak can remain. Squid beaks are hard and can accumulate in the stomachs of predators like whales. They can also sink and persist. If a crab dies, its shell can remain. But if a jelly-like organism dies, it often dissolves quickly. It becomes food for microbes. It becomes part of the water. It leaves no hard evidence. That means if you wanted to prove the existence of a large unknown gelatinous creature, you would need to film it alive. You would need to observe it directly, because you won't find its skeleton. and that makes gelatinous mysteries persistent. Even if a large jelly existed in the deep ocean, it could go undetected for a long time. Now, to connect this back to giant shadows, imagine how a gelatinous organism might appear on camera. A transparent body might only be visible as a faint outline. Tentacles might catch light and look like thin lines. A Siphonophore might look like a drifting rope. A comb jelly might reflect light in a way that looks like a moving shimmer. And if the camera light is narrow, you might only see part of it. That partial view is perfect for creating confusion. A long animal might look like it has no end. A drifting colony might look like a single giant creature. A jelly might look like a floating shape that doesn't move like a fish. And because we don't have many reference points, the size can be misjudged. This is why some deep sea footage feels so eerie. Not because it shows monsters, but because it shows organisms that don't behave like the animals we're used to. They drift, they pulse, they extend long structures into darkness. They don't have obvious faces, they don't have obvious fins, they look like living shapes. Now, there's another layer to this. Some gelatinous organisms produce light. Bioluminescence in gelatinous animals can be used for defense, communication, or prey attraction. Some jellies flash when disturbed. Some siphonophores have glowing parts. Some comb jellies can produce light in certain conditions. In the deep ocean, light is rare, so a glowing organism becomes a signal. It can startle predators. It can confuse prey. It can attract attention. And if you're a human watching a camera feed in darkness, a sudden glow can feel like a creature announcing itself, but it can also feel like a warning. Now, you might be wondering why gelatinous life matters so much for our topic, about prehistoric creatures in the Mariana Trench. It matters because it represents a category of life that is both ancient and hard to document. If the trench is hiding anything that feels prehistoric, it might not be a giant reptile. It might be an ancient gelatinous lineage. It might be a siphonophore species we haven't recorded. It might be a deep jelly that lives in a narrow depth range. It might be a comb jelly adapted to Hadal conditions. It might be something that doesn't leave evidence behind. And because it doesn't leave evidence, it can remain unknown. Now let's take a step forward into another category of deep sea life that feels prehistoric for a different reason. Not because it's soft and ghostly, because it's built like a weapon. Teeth, light, predators that look like they were designed to scare anything that gets too close. The deep sea has fish that are so specialised for hunting in darkness that they almost look like they belong in a horror movie. And one of the most striking examples is the dragonfish. So next, we're going to talk about the dragonfish problem, what makes these predators so extreme, and why the deep ocean can produce creatures that feel ancient and monstrous without needing any exaggeration at all. There are some animals that look strange in a charming way. A sea otter floating on its back holding hands, a frog with big eyes, a tiny fish with a face that looks permanently surprised. And then there are animals that look like they were built for a world where kindness never evolved. The dragonfish belongs in that second category. Even the name sounds like it's trying too hard, like something from a fantasy novel, but dragonfish are real. They live in the deep ocean, and their biology is so intense that it feels like it should be fictional. When people talk about deep-sea monsters, they often imagine something unknown, something undiscovered, something hiding. But the dragonfish is one of those creatures that reminds you the deep sea doesn't need to hide anything to be terrifying. It can put the truth right in front of you, and the truth is already extreme. Now, dragonfish aren't trench-bottom animals in the strict Hadal sense. They are typically found in deep mid-water zones, often hundreds to thousands of meters down depending on the species. But they are part of the deep ocean world that surrounds trenches, and they represent a category of predator that thrives in darkness. And their existence matters for our topic because it shows what deep water can do to a predator's design. It can turn it into something that looks prehistoric, not because it's old, but because it's optimized for a harsh environment in a way that feels brutal and ancient. The dragonfish problem is simple to state. How do you hunt in a place where there is no light? Because on the surface, hunting is often visual. You see prey, you chase it, you ambush it, you track movement, you use eyes. In the deep ocean, eyes still matter, but darkness changes the rules. It turns hunting into a game of sensing, waiting, and using light in ways that don't exist on the surface. The dragonfish solves this problem with three main tools: teeth, light, and a body built to make the most of rare opportunities. Let's start with the teeth, because they're the first thing anyone notices. Dragonfish teeth are long, needle-like, and sharp. They curve inward, designed to prevent prey from escaping once caught. In many deep-sea fish, teeth are exaggerated because prey encounters are rare. When you finally catch something, you cannot afford to lose it, so the mouth becomes a trap. Dragonfish mouths are often large relative to their bodies. Their jaws can open wide. Their teeth can look like a cage. But the most unsettling part is that many dragonfish teeth are transparent. That sounds like a small detail until you realize what it means. If a dragonfish is using light to lure prey, and its teeth are transparent, then the prey might not see the trap until it's already inside it. A mouth full of invisible needles. That is not a metaphor. That is an adaptation. It's a reminder that evolution in the deep sea is not gentle. It is practical. It is cold in the way the water is cold. Now, why would teeth be transparent? Because in the deep ocean, even small amounts of light matter. Many deep-sea animals produce bioluminescence. If a predator's teeth reflect light, they could give away its presence. So transparent teeth reduce glare and reflection. They make the predator harder to detect. It's camouflage, but not the kind we're used to. It's camouflage in a world where light is rare and precious, and any reflection can be the difference between eating and starving. Now let's talk about the light, because dragonfish are famous for their bioluminescence. Many deep-sea animals produce light. Some use it for communication, some use it to confuse predators, some use it to attract prey. Dragonfish use it for hunting. They have photophores, light-producing organs, along their bodies. They can create patterns of light. They can glow faintly. They can use light as a lure. But there is one feature that makes some dragonfish especially strange. Some species can produce red light. This is a big deal because red light doesn't travel far in water. In the upper ocean, red wavelengths are absorbed quickly, which is why deep water looks blue. Red disappears first. So in the deep ocean, most animals are not adapted to see red, because there is no red light down there naturally. If you produce red light, you may be producing a wavelength that your prey cannot see. That means you can shine a light on prey without them realizing they're being illuminated. It's like having night vision in a world where no one else knows what night vision is. This is one of the most effective stealth hunting strategies imaginable. A dragonfish can potentially use red bioluminescence like a private flashlight, scanning for prey while remaining invisible to animals that cannot detect red wavelengths. Now, not all dragonfish species do this, but the fact that any do is enough to make you rethink how complex deep-sea hunting can be. It also adds to the prehistoric feeling. Because red light in the deep feels like a secret technology. It feels like an ancient predator trick, something that evolved in darkness and stayed hidden from surface life. Now let's talk about the body design. Dragonfish bodies are often long and slender, adapted for drifting and sudden strikes. They don't need to be fast swimmers in open water the way tuna are. They need to conserve energy. Energy is everything in the deep. Food is scarce. Encounters are rare. Movement costs calories. So many deep-sea predators have low-energy lifestyles. They drift. They wait. They strike when prey comes close. Dragonfish fit this pattern. They don't chase for long distances. They use stealth, lures, and sudden attacks. And that hunting strategy shapes their anatomy. Large mouths, long teeth, expandable stomachs in some cases, light organs for attraction and camouflage, sensory systems tuned to faint signals. This is how you get a creature that looks like a nightmare but functions like a highly efficient machine. Now, the dragonfish problem also includes another element that makes the deep sea feel prehistoric. The deep ocean is full of predators that can swallow prey larger than themselves. This seems impossible until you remember how rare food can be. If you only get occasional meals, you want to take the biggest meal you can handle. So deep-sea fish often have jaws that can open wide, stomachs that can stretch, and bodies that can accommodate large prey. The gulper eel is a classic example with its enormous mouth. The viperfish is another, with long fangs. Dragonfish fit into this category of maximum opportunity predators. It's not about elegance, it's about efficiency. Now, when we talk about dragonfish, we should also talk about their environment. Dragonfish live in the deep water column, often in the mesopelagic and bathypelagic zones. This is a world of darkness, but not necessarily the crushing pressure of the trench bottom. Still, the conditions are harsh. Cold temperatures, low food availability, sparse distribution of prey, the need for stealth and energy conservation. So dragonfish represent a deep ocean predator blueprint, a set of traits that are useful in darkness. And this blueprint is not unique to dragonfish. Many deep-sea fish share similar traits. The deep ocean repeatedly produces predators with big mouths, sharp teeth, and bioluminescence. This repetition is important because it tells us something about evolution. In the deep, there are only so many ways to solve the problem of finding food. So certain designs appear again and again. That can make the deep feel prehistoric, because it suggests an environment where ancient solutions persist. Not because they're old, but because they are fundamental. Now let's address the nightmare biology part of the title, because dragonfish have other features that feel extreme. Some deep-sea fish have fragile bodies that would not survive in shallow water. Some have eyes adapted to detect tiny amounts of light. Some have sensory systems tuned to vibrations and chemical cues. Dragonfish, depending on species, can have large eyes relative to their heads, designed to detect faint bioluminescence. They may also have lateral line systems that detect water movement, helping them sense prey. In darkness, your body becomes a sensor array. You don't just look, you feel the water, you detect changes, you respond. That sensory world is hard for us to imagine because we rely so heavily on sight. But for deep-sea predators, the environment is full of information, even when it looks empty to us. Now, here's where dragonfish connect back to the Mariana Trench and the idea of prehistoric creatures hiding there. Dragonfish show us that deep water can produce predators that feel ancient and monstrous without being enormous. They are not giant. They are not the size of a car. But they feel like monsters because their design is so specialized and so intense. This is important because it suggests that the trench's prehistoric creatures might not be giant at all. They might be small to medium-sized animals with extreme adaptations. They might be predators that look like they belong in another era. They might be creatures that rely on stealth and sensory tricks. They might be animals that rarely come near our cameras. Because the deep ocean is not just hiding size, it's hiding design. Now, dragonfish also highlight another reason deep-sea mystery persists. Deep-sea animals often look different when they are brought to the surface. Pressure changes can distort their bodies, their tissues can collapse, their colours can change, their shape can be altered by decompression. So even when we catch deep-sea fish, we may not be seeing them as they truly are in their natural environment. A dragonfish in the deep is a predator moving through water at high pressure, supported by buoyancy. On the surface, it becomes a fragile specimen under gravity, out of its element. So our perception of deep-sea creatures is often incomplete. Now, let's zoom out. If dragonfish represent one extreme predator design, what other predators in the deep carry ancient traits? Sharks, of course, are one, but there are also deep-sea sharks that feel like they belong to an ancient predator blueprint. And when you start looking at deep-sea sharks, you realize something. The ocean doesn't just have predators, it has predators that have been refining their design for hundreds of millions of years. So next we're going to talk about deep-sea sharks and the ancient predator blueprint, and why sharks remain one of the most plausible candidates for prehistoric feeling creatures lurking in deep waters, even if they aren't living at the very bottom of the trench. Sharks have a strange effect on the human brain. Even people who love sharks, people who study them, people who know the facts, still tend to feel a small shift in their body when they see one move through water. It's not always fear, sometimes it's awe, sometimes it's respect, sometimes it's that quiet awareness that you're looking at a predator that didn't need humans to exist in order to become perfect at what it does. Because sharks are not new. Sharks are ancient in a way that's hard to fully absorb. Their lineage stretches back more than 400 million years. That means sharks were already swimming in Earth's oceans long before dinosaurs existed. They lived through multiple mass extinctions. They outlasted entire branches of life that once dominated the planet. So when we talk about prehistoric creatures that might still be hiding in deep ocean environments, sharks are one of the most grounded places to start. Not because there's a secret megalodon in the Mariana Trench, but because sharks themselves are living proof that ancient predator designs can persist. And when you move into the deep sea, sharks start to look even more prehistoric. Not necessarily larger, not necessarily more aggressive, but more unfamiliar. More like the ocean has kept certain models in storage and occasionally lets one glide past your imagination. Now, to be clear, the deepest parts of the Mariana Trench, the Hadal zone, are not known as shark territory. The pressure is extreme, and the food supply at the very bottom is limited. Most sharks are not built to live at 8,000 to 11,000 meters, but deep-sea sharks do exist, and they live in the deep ocean regions that surround trenches. They live on slopes, in deep basins, and in cold, dark waters that are still far beyond the reach of casual human observation. And that matters, because the trench doesn't exist in isolation. It's part of a larger deep-sea world, and that world is where deep-sea sharks thrive. So if you're imagining prehistoric predators hiding in the darkness near the Mariana Trench, you don't necessarily need to imagine them sitting at the bottom of Challenger Deep. You imagine them patrolling the deep slopes, the midwater layers, the edges where the trench meets the broader ocean, because those are places where a large predator can exist. And sharks have the right blueprint. The ancient predator blueprint is simple, but it's brutally effective. A streamlined body for efficient swimming, a skeleton made of cartilage, lighter than bone, powerful muscles, multiple rows of replaceable teeth, highly developed senses, a metabolism that can operate in a range of conditions. This design has been refined over hundreds of millions of years, and it keeps working because water is a stable medium. The ocean hasn't changed its basic physics. Water still resists movement. Prey still needs to be caught. Energy still needs to be conserved, so sharks remain relevant. Now, what makes a shark a deep-sea shark? It's not just depth, it's a suite of adaptations for living in cold, dark, low-energy environments. Deep-sea sharks often have slower metabolisms. They may move more slowly. They may have larger livers filled with oils that help with buoyancy. Their eyes may be adapted to low light. Some have sensory systems tuned to detect faint signals in darkness. And many deep-sea sharks have an appearance that feels older, heavier, more primitive, even though they are fully modern animals. They can look like they belong in an ancient ocean. One of the most famous deep-sea sharks, in terms of prehistoric vibe, is the frilled shark. The frilled shark is often described as eel-like. Its body is long and flexible, its head is broad, its mouth contains rows of sharp, trident-like teeth that point inward. It has gill slits that give it a frilled appearance, which is where the name comes from. It looks like something that could have been swimming in the ocean when the continents were arranged differently. It lives deep, usually hundreds to over 1,000 meters down, and it's rarely seen alive. Most encounters happen when one is caught accidentally in deep fishing nets or spotted by submersibles. Because it's rare, it has become part of the deep-sea monster conversation. People see a frilled shark and assume it must be an undiscovered creature, because it looks so strange. but it's not undiscovered, it's just deep. And that's an important lesson. The deep ocean can make real animals feel like myths simply because we don't see them often. Now, another deep-sea shark that carries an ancient feeling is the goblin shark. The goblin shark is famous for its protrusible jaws. Its snout is long and flattened. Its skin can appear pale or pinkish because of the blood vessels visible through the tissue. It looks less like a sleek predator and more like a creature built for ambush. When a goblin shark strikes, its jaws can extend forward rapidly, snapping prey with a sudden mechanical motion that looks almost unnatural. This is not a trench shark, but it is a deep water shark, and it shows the kind of specialized hunting adaptations that deep environments can produce. Again, the deep doesn't just create bigger predators, it creates weirder predators. Then there are the 6-gill and 7-gill sharks. These sharks have more gill slits than most modern sharks, which usually have 5. 6-gill sharks, for example, are large, deep water sharks that can reach impressive sizes. They have broad heads, large bodies, and a slow, heavy movement that feels ancient. They're often found in deep waters, sometimes near continental slopes. They are scavengers and predators, feeding on fish, squid, and carrion. 6-gill sharks are another reminder that large predators can exist in deep environments, and they can remain mostly unseen because humans rarely go there. Now let's talk about the sleeper sharks, because they are one of the most interesting groups when it comes to the prehistoric feeling. Sleeper sharks include the Greenland shark and the Pacific sleeper shark. These sharks are known for their slow movement, cold water habitats, and deep living tendencies. The Greenland shark is the most famous, largely because of its lifespan. It is believed to be one of the longest-lived vertebrates on Earth, potentially living for centuries. Imagine that for a second. A shark swimming through cold deep water, moving slowly, living through generations of human history, without ever knowing we existed. That is not just ancient in lineage, that is ancient in lived experience, and that long lifespan is connected to deep-sea living. Cold temperatures slow metabolism. Slow metabolism slows growth and aging. A shark that lives in cold, deep water can afford to live slowly. Now, sleeper sharks also have another feature that adds to their eerie reputation. Some Greenland sharks have parasites attached to their eyes, which can cause cloudiness or partial blindness. That gives them a ghostly appearance. A slow-moving shark with cloudy eyes drifting through dark water is the kind of image that sticks in the mind. And even though the Mariana Trench is far from the Greenland shark's home, the concept matters. It shows how deep environments can support ancient-feeling predators with unusual life histories. Now, what about the idea of prehistoric sharks hiding in the deep? There's a reason people keep bringing up Megalodon, even though it's not scientifically supported as a living species today. Megalodon was a massive prehistoric shark, likely reaching lengths far beyond any modern shark. Its teeth are found as fossils, and those teeth are huge. They make the imagination run instantly. If a shark like that existed today, the deep ocean would seem like the only place it could hide. But the problem is not hiding. The problem is ecology. A massive predator needs massive food resources. It needs a stable supply of large prey. The deep ocean, especially trench environments, does not offer that kind of abundance. Also, a predator that large would leave evidence. It would interact with prey populations. It would leave bite marks. It would be seen or detected more often. So the idea of a living megalodon in the Mariana Trench is extremely unlikely. But here's the twist. You don't need megalodon for the deep ocean to have prehistoric shark energy. Modern deep-sea sharks already carry that. They are ancient lineages. They are rarely seen. They live in environments humans barely explore. They have unusual features. They have slow, deliberate movement. They are the closest thing we have to prehistoric predators that are still active in today's oceans. And because they live deep, they can remain mysterious. Now let's talk about why deep-sea sharks can survive in such harsh environments. Food scarcity is one challenge. Deep-sea sharks often have opportunistic diets. They will eat fish, squid, carrion, and whatever else they can find. Some are scavengers as much as they are hunters. They don't waste energy. Their buoyancy systems help them float without constant swimming. Many sharks have large livers filled with oil, which reduces their density and helps them maintain position in the water column. Their senses are tuned to detect prey in darkness. Sharks can detect electrical signals from muscle movement. They can detect chemical cues in water. They can sense vibrations, so even in darkness they can locate food. And because deep environments are cold, their metabolism can be slower, reducing energy demands. This combination, efficient movement, powerful senses, opportunistic feeding, slow metabolism, makes deep-sea sharks well suited to deep living. Now, let's connect this to the Mariana Trench again. The trench is surrounded by deep slopes and deep basins. These regions can host deep-sea sharks. A shark might not need to live at the bottom of the trench to be part of the trench ecosystem. It could patrol the edges, feeding on deep fish, squid, and carrion drifting down. And because the trench is a natural funnel for sinking material, it can attract scavengers, which can attract predators. So the trench region can be a hunting ground. Not necessarily a permanent home, but a place where deep predators might pass through. Now, one of the most interesting aspects of deep-sea sharks is how rarely humans encounter them. We know they exist, but we don't see them often. They live far below recreational diving depths. They often avoid bright lights. They may be spread out over large areas. They may move slowly and quietly. So a deep-sea shark can be a perfect candidate for giant shadow sightings. A large shape moving through darkness, a sudden appearance on sonar, a fleeting image on a camera, and because sharks already carry prehistoric associations, people interpret the sighting as something ancient. Now here's a final point that matters for our larger story. Sharks are not the only ancient predators in the deep, but they are one of the most iconic, and their presence in deep waters shows that the ocean still supports predators built on ancient blueprints, which means the idea of prehistoric feeling creatures hiding in deep environments is not just a story, it's a reality, in the sense that ancient lineages are still here, still hunting, still moving through water that humans rarely see. Now, if deep-sea sharks represent one kind of ancient predator, there's another kind that feels even more eerie in its own way, not because it looks like a monster, because it looks like it's barely moving at all. A shark that seems to sleep while it swims, a predator that lives slowly, patiently, as if time means something different down there. So next, we're going to focus on the sleeper shark specifically, and why their slow, cold existence feels like one of the closest things we have to a prehistoric creature still alive in the modern ocean. If you wanted to build a predator for the deep ocean and you weren't interested in speed, you wouldn't make it sleek and aggressive. You wouldn't make it look like a torpedo. You wouldn't make it a constant hunter burning energy every second. You'd make it slow, you'd make it heavy, you'd make it patient. You'd make it the kind of animal that can drift through darkness without looking like it's in a hurry to be anywhere. That's the sleeper shark. And the reason sleeper sharks feel so unsettling is not because they look like monsters in the usual sense. They don't have the exaggerated teeth of a dragonfish. They don't have a glowing lure. They don't look like they were designed to scare you on purpose. They feel unsettling because they look like they've been here forever. Like the ocean made them early, realised they worked, and never bothered to redesign them. Sleeper sharks are part of the family Somniosidae, and they include species like the Greenland shark and the Pacific sleeper shark. There are others too, but these are the ones that most often show up in conversations about deep, cold predators. They live in cold waters, often at depth. They can move between shallow and deep environments depending on region and season, but they are strongly associated with the kind of dark, cold water that humans rarely enter. And they have a reputation that is both simple and strange. They are slow, they are old, they look ancient, and somehow they still eat. Now, if you've ever seen footage of a Greenland shark, You might have noticed something that feels almost wrong. It doesn't swim like a typical shark. It doesn't look sharp and alert. It looks like it's half asleep. It glides. It drifts. It moves with a kind of calm that makes you wonder how it catches anything at all. That's where the name sleeper shark comes from. It's not literally asleep, but its movement and behaviour can look sluggish compared to other sharks. And the first time you see one, you might assume it's sick, or dying, or injured. But then you realise this is normal. This is what it's supposed to look like. This is the strategy. Because in the deep, speed is expensive. Every movement costs energy. Every chase burns calories. Every burst of acceleration demands oxygen and muscle power. In a world where food can be scarce, the best predator is not always the fastest. Sometimes it's the one that can survive on very little. Sleeper sharks are built for that. They have slow metabolisms, especially in cold water. Cold temperatures slow biochemical reactions. That slows movement, growth, digestion, and everything else. To a human, it looks like the animal is moving through thick syrup. But to the shark, it's just normal life. Now, the Greenland shark is the most famous sleeper shark, and it's famous for one main reason: its lifespan. Scientists have estimated that Greenland sharks can live for centuries. Some research suggests individuals can live 300 to 500 years, making them among the longest-lived vertebrates ever discovered. That's not just a fun fact, that's a complete shift in perspective. A Greenland shark could be alive today that was born before the Industrial Revolution, before electricity became common, before the modern world as we know it. It could have been swimming in cold water, while humans were still travelling primarily by sail, and it would have no idea that anything changed. Because down there, the world doesn't change quickly. This is one of the reasons sleeper sharks feel prehistoric, not because they are fossils walking around, but because they exist on a timescale that feels ancient. They are living animals that experience the world slowly. Now, the Mariana Trench is not home to Greenland sharks. They are Arctic and North Atlantic animals. But the idea of sleeper sharks matters for our topic, because it shows what deep, cold environments can do to a predator's life history. They can stretch time. They can create animals that grow slowly, mature late, and live long. And the deep ocean around the Mariana Trench is cold. Not Arctic cold, but cold enough to slow metabolism. Deep-sea environments tend to have stable, low temperatures, so the deep can support long-lived animals. And long-lived animals feel prehistoric because they carry years inside them. Now, what about the Pacific sleeper shark? The Pacific sleeper shark is less famous than the Greenland shark, but it's still a remarkable animal. It lives in the North Pacific, often at depth, and can reach large sizes. It has the same general sleeper shark vibe: slow, heavy, built for cold water, capable of scavenging and hunting. Pacific sleeper sharks have been found with all kinds of prey in their stomachs, including fish and even marine mammals in some cases. That leads to a question that always comes up. How does a slow shark catch anything? The answer is that sleeper sharks are not limited to one feeding strategy. They can scavenge, they can ambush, they can take advantage of weak or injured prey, they can feed on carcasses that sink, they can possibly catch sleeping or resting animals, they can also hunt when needed, even if they aren't built for constant high-speed pursuit. Slow does not mean helpless. Slow means efficient, and in the deep, efficiency wins. Now, sleeper sharks are also known for something else that adds to their eerie reputation: their eyes. Greenland sharks often have parasites attached to their eyes, particularly a copepod called Omatocoita elongata. These parasites can attach to the cornea and cause damage, sometimes leading to partial blindness. So you might see a Greenland shark with cloudy eyes, drifting through cold water, moving like it's in a trance. That image is powerful. It looks like a creature that has lived too long, like something that has been worn down by time and still keeps moving anyway. And even though that parasite relationship is specific, it contributes to the mythic feel of sleeper sharks. Now, let's connect this to the deep ocean's ancient predator blueprint. Sleeper sharks, like other sharks, have cartilage skeletons, replaceable teeth, and strong sensory systems. But they also have traits that fit deep living. Large, oily livers for buoyancy, thick bodies for energy storage, slow metabolism for survival in low-food environments, a willingness to eat a wide range of prey, and an ability to move between depths. This makes them extremely resilient, and resilience is what keeps lineages alive over long periods. Now, when people talk about prehistoric creatures hiding in the Mariana Trench, they often imagine something enormous and unknown. But sleeper sharks suggest a different kind of prehistoric survival. Not a hidden giant, a hidden endurance, a predator that doesn't need to be dramatic to be ancient, a predator that can survive in a stable environment for centuries, quietly feeding, quietly moving, quietly existing. Now, here's another reason sleeper sharks feel prehistoric: their faces. Some deep-sea sharks have facial features that look less modern to us. They can have blunt snouts, small eyes, heavy jaws, a body that looks like it belongs to an older design. That's not scientific language, but it's how it feels visually. And the reason it feels that way is because we're used to seeing sharks like great whites, which are fast, sleek, and expressive in their movement. Sleeper sharks don't perform that way. They don't advertise their power. They just are. Now, if you're listening and thinking, this is interesting, but what does it have to do with the Mariana Trench? Here's the connection. The Trench region is part of the Deep Pacific ecosystem. The Deep Pacific includes many shark species, including deep water sharks that we still know relatively little about. We do not have constant monitoring. We do not have complete population data. We do not have full behavioural understanding. So even if sleeper sharks themselves are not trench bottom residents, the deep ocean environment that produces sleeper sharks is the same kind of environment that surrounds trenches: cold, dark, stable, low energy. And that environment is exactly the kind of place where ancient-feeling predators can persist. Now, there's another important detail. Deep-sea sharks are often caught as bycatch in deep fishing operations. This is one of the main ways humans encounter them, but that also means our knowledge is biased toward areas where fishing happens. If a deep region is rarely fished, its shark community might be less documented. The Mariana Trench region is not a major fishing ground, in the same way some continental slopes are, which means fewer accidental catches, fewer specimens, fewer encounters. That leaves room for unknowns. Again, not necessarily giant unknown monsters, but species diversity we haven't fully mapped. Now, sleeper sharks also show something else that matters for the prehistoric feeling. They don't need to be aggressive to be dangerous. A Greenland shark can still bite. A Pacific sleeper shark can still tear flesh. They are predators and scavengers with powerful jaws. But their danger is quiet. It's the danger of a creature that doesn't waste energy, that waits, that feeds when it can, that survives when others would starve. That kind of predator feels older than the flashy kind. It feels like the ocean's original plan. Now, there's one more layer to the sleeper shark story that is worth mentioning. We still don't fully understand their reproduction. We don't know exactly where they give birth. We don't know how often they reproduce. We don't know the details of their mating behaviour. This is common in deep-sea animals. Their lives are hard to observe, so sleeper sharks carry mystery, not because they are mythical, but because we haven't watched them long enough. And mystery is what makes an animal feel prehistoric. Because the prehistoric world is, by definition, a world we didn't see. We reconstruct it from fragments. With sleeper sharks, we're doing something similar. We know they exist, we know their general traits, but their full life story is still incomplete. Now, with sleeper sharks in mind, we're ready to move into one of the most legendary categories of deep ocean mystery: cephalopods. Squid and octopus are already strange, even in shallow water. They're intelligent, flexible, and built unlike anything with bones. In deep water, cephalopods can become even more mysterious. And the question people always ask, sometimes joking, sometimes seriously, is the same. Could something bigger still exist? So next, we're going to talk about cephalopod legends, what we know about giant squid and deep ocean cephalopods, and why the deep sea remains one of the only places on Earth where something bigger still feels possible. Cephalopods are the kind of animals that make you realise nature doesn't need to follow familiar templates. They don't have bones, they don't have fur, they don't have scales in the way fish do, they don't even move the way most animals move. They change colour, they squeeze through gaps, they use jet propulsion, they can solve problems, they can learn, they can react with a kind of awareness that feels almost uncomfortable when you remember they're not mammals, and that's in shallow water. In deep water, cephalopods become something else entirely, because the deep ocean gives them what they seem built for: space, darkness, distance, and the ability to exist without being watched. So when people ask, could something bigger still exist? They're usually talking about cephalopods, even if they don't realise it. Squid, in particular, have become the default candidate for deep-sea legends, because they already have a history of being underestimated. For a long time, giant squid were treated like sailor stories, not because people were stupid, but because the ocean didn't provide easy evidence: a few tentacles on a beach, a damaged body, a beak in a whale's stomach, a story told with wide eyes. It wasn't until modern technology improved that we started to get clearer confirmation, footage, photos, observations of living animals, and once that happened, the deep ocean imagination didn't calm down, it got louder, because the moment you confirm that giant squid exists, you also confirm something else. The ocean can hide large animals for a long time, not forever, but long enough for humans to build myths around them, so the question becomes less ridiculous. Could there be something bigger? Now, to keep this grounded, we need to separate three things: what we know exists, what we strongly suspect exists, and what people want to exist. We know giant squid exist. They are real animals, part of the genus Architeuthis. They can reach lengths that are impressive, with long tentacles and a body designed for deep water. We know colossal squid exist too, Mesonychoteuthis hamiltoni. Colossal squid are often described as heavier and more robust than giant squid. They have thick arms, large hooks, and enormous eyes. Colossal squid are less often seen alive, but they are known from specimens and from evidence found in predator stomachs. So the deep ocean already has squid that qualifies legendary. And these squid are not shallow water animals that occasionally wander deep. They are deep water specialists. They live in the kind of environment humans rarely observe. Now, why do cephalopods make such good candidates for something bigger? Because of how they're built. A squid's body is flexible. It can be large without needing a heavy skeleton. It can grow to great size without being weighed down by bone. It can move through water with jet propulsion. It can use tentacles to capture prey at a distance. In water, buoyancy reduces the weight problem that land animals face. A large squid doesn't have to support itself against gravity the way a large land animal does. It can float. It can hover. It can drift. That makes large size more plausible. Also, cephalopods can be elusive in a way that many fish are not. They don't have to constantly swim forward like sharks. They can remain still. They can hide in darkness. They can use camouflage. They can avoid lights. And they can die without leaving much trace. If a large squid dies in deep water, it might be eaten quickly. It might sink and be consumed. Its soft tissue might disappear. Only the beak might remain. And even that could be swallowed by something else. So cephalopods have the perfect combination for legends. They can be large. They can be rare. They can be hard to film. They can leave minimal evidence. Now, what about the Mariana Trench specifically? The trench itself is extremely deep, and the deepest Hadal zone is a harsh environment for large active predators, because food is limited. A massive squid living at the bottom of the trench full time would need enough energy to sustain itself, and that's not guaranteed. But the trench is surrounded by deep waters that are more plausible habitats for large squid. The slopes, the deep pelagic zones, the regions where prey like deep fish and other cephalopods exist. So if you're looking for large cephalopods near the Mariana Trench, you don't focus only on the deepest point, you focus on the broader deep ocean environment around it, because that's where a large squid could hunt. Now, one of the reasons squid feel prehistoric is that they represent an ancient style of predator. Not ancient in the sense of being unchanged, but ancient in the sense of being fundamentally different from vertebrate predators. A shark is a spine and cartilage and muscle. A squid is a soft body with arms, suction, hooks, and a beak. A squid's mouth is not at the front of its head the way ours is, it's in the centre of its arms. Its beak is hidden until it bites. Its arms can move independently. Its tentacles can shoot out to grab prey. This is not the kind of predator we evolved alongside on land, so it feels alien. And anything that feels alien tends to feel prehistoric, because prehistoric life is often imagined as strange and unfamiliar. Now let's talk about the kraken, because even if you don't take the myth literally, it matters culturally. The kraken is one of the most famous sea monster legends, often described as a giant squid or octopus capable of dragging ships down. It's exaggerated, but it likely has roots in real encounters with large squid. Sailors may have seen tentacles, they may have seen bodies, they may have seen arms wrapped around prey, they may have seen a squid surface briefly. In a world without underwater cameras, a rare encounter becomes a story, and stories grow. So the kraken is not scientific evidence, but it's a sign that humans have been aware of large cephalopods for a long time, even if they didn't have the tools to prove it. Now, could something bigger exist than what we know? The honest answer is that it's possible, but not in the way people usually imagine. It's unlikely that there is a single species of truly gigantic squid that is dramatically larger than giant squid and colossal squid, living undetected in large numbers. A creature that large would need enough prey, and it would likely be detected through predator diets, strandings, or fishing encounters more often. But it is plausible that there are species we haven't documented well. There may be deep water cephalopods that are rare, or that live in specific regions, or that have life cycles we don't understand. There may be large individuals of known species that reach sizes we haven't recorded. There may be species that exist at depths we rarely explore. And because cephalopods are fragile and hard to capture intact, they can remain underrepresented in our data. So the something bigger idea might not mean a monster squid the size of a skyscraper. It might mean a species that is larger than expected, or more widespread than expected, or more behaviourally complex than expected. Or it might mean that the deep ocean contains cephalopods that behave in ways we haven't observed. Now here's something important. Cephalopods are not just big arms and tentacles, they're also intelligent. Octopuses are famous for problem-solving, tool use, and escape behaviours. Squid are less studied in terms of intelligence, but they still have complex nervous systems and behaviours. So when people imagine a giant cephalopod in the deep, they often imagine something not just large, but aware. And that's where the fear becomes deeper. Because a large predator is one thing. A large predator that can think is another. Now, do we have evidence of deep ocean cephalopods displaying advanced intelligence? Not in the way we can easily measure, because observing them is difficult, but the potential is there. Cephalopods have large brains relative to many other invertebrates. They have complex eyes. They have sophisticated behaviours. So the deep ocean could contain cephalopods that we don't understand, not just in size, but in behaviour, and that keeps the legend alive. Now let's talk about why cephalopods are so hard to study. First, they live deep. Second, they are fast and elusive. Third, they are soft-bodied and fragile. Fourth, they can avoid nets and traps. Fifth, their bodies can be damaged by decompression. So even when we catch deep-sea squid, we may not catch them in good condition. We may not know what they look like alive. We may not know their natural behaviour. A dead squid on the surface is not the same as a living squid in its environment. This is why footage of living giant squid was such a big deal. It gave us a glimpse of the animal as it actually exists. Now, Another reason cephalopods feel connected to the trench is that the trench environment includes deep water columns where squid can move vertically. Squid are not necessarily tied to the seafloor. They can roam the water column following prey. That means a large squid could pass over the trench without living on the trench floor. It could exist in the deep water above, moving through darkness, hunting fish and other squid. And if it did, it would be hard to detect, because we don't monitor that space constantly. Now, there's another piece of the cephalopod legend puzzle: sperm whales. Sperm whales are deep-diving predators that feed primarily on squid. They can dive to great depths, sometimes over 1,000 meters, and they hunt in darkness using echolocation. Sperm whales often have scars, circular marks on their skin, which are believed to come from squid suction cups. Those scars are physical evidence of battles in the deep. That alone is enough to make your imagination work. Because if a whale the size of a bus comes to the surface covered in scars, you naturally wonder what caused them. Giant squid and colossal squid are likely responsible for many of those scars. So we know that large cephalopods fight large predators in the deep. That's not a myth, that's ecology. Now, could sperm whales be encountering squid larger than we know? It's possible that there are rare individuals or species that we haven't documented well. But again, it's more likely that the deep contains variation and unknown diversity, rather than a single hidden super monster. Now, let's connect this to the Mariana Trench again. The Mariana region is deep, remote, and not heavily observed. It has deep water columns where squid could exist. It has deep fish and other prey species. It has currents and ecological pathways that could support cephalopods. So the idea of large squid near the trench is not far-fetched. What is far-fetched is the idea of a giant squid living at the very bottom of Challenger Deep like a dragon in a cave. Squid are not cave monsters. They are mobile predators. They move, they roam, they hunt. So if something big exists, it likely moves through the deep ocean rather than sitting in one spot. Now, here's the most important thing about cephalopod legends. They don't require us to invent anything new. The real animals are already legendary. A colossal squid with eyes the size of dinner plates is already a creature that sounds fictional. A Siphonophore longer than a blue whale is already a creature that sounds fictional. A dragonfish with transparent teeth and red light is already a creature that sounds fictional. So the deep ocean doesn't need us to exaggerate. It just needs us to look. And when we look, we realise the ocean has been doing this the whole time. Now as we move forward, we're going to shift from predators to a different idea. The trench as a refuge. A place where life can hide not because it's trying to scare us, but because it's trying to survive. Because if the deep ocean can shelter ancient lineages, then the Mariana Trench might be less like a monster lair and more like a hidden sanctuary. A place where extinction doesn't reach as easily. A place where certain creatures might have persisted while the surface world changed above them. So next we're going to talk about the trench as a refuge, and why hiding from extinction might be one of the most realistic explanations for why the deep ocean still feels prehistoric today. Extinction is one of the most normal things that happens on Earth, even though it never feels normal when you think about it. Species appear, they spread, they adapt, and then, eventually, many of them vanish. Sometimes slowly, over long stretches of time, sometimes suddenly, in a geological blink. And most of the time, extinction doesn't look dramatic. It doesn't look like a meteor striking the planet. It looks like a species failing to reproduce enough. It looks like food becoming scarce. It looks like water chemistry shifting. It looks like a habitat changing until it no longer fits the body that evolved for it. On the surface, the world changes quickly. Climate shifts. Coastlines move. Ice comes and goes. Forests expand and collapse. Oceans warm and cool. Oxygen levels rise and fall. Entire ecosystems can be rearranged. But the deep ocean is different. The deep ocean changes too, but it often changes more slowly, and it stays stable in ways the surface doesn't. It remains cold. It remains dark. The temperature doesn't swing wildly from season to season. Sunlight never appears and disappears. The daily cycle that shapes life on land doesn't reach the trench. So when you look at the Mariana Trench, it starts to feel less like a pit and more like a shelter, a refuge. Not because it's gentle, because it isn't. It's harsh, it's crushing, it's cold, it's starved. But because it is consistent. And consistency can be a kind of safety. That's the strange truth of the trench. It is one of the most extreme environments on Earth, and yet it can also be one of the most stable. And stability is exactly what can allow life to persist when the rest of the world is changing. So if you want to understand why the deep ocean still feels prehistoric, the trench as refuge idea is one of the best explanations. Not a monster story, a survival story, because the trench can function like a hiding place from extinction. Now, this doesn't mean the trench is untouched by global events. It's not sealed off. The ocean is connected. Currents move water. Chemistry changes can spread. Major disruptions can reach deep environments, but the deep ocean is buffered. The temperature down there doesn't jump up and down quickly. The light doesn't change. The habitat doesn't get bulldozed by storms. It doesn't burn. It doesn't freeze and thaw. It doesn't experience drought. So when surface ecosystems get wiped out or reorganized, deep ecosystems can sometimes persist with less disruption. That's why the deep sea is often described as a place of ancient lineages, not because nothing changes, but because change is slower. And slow change gives life a chance to hold on. Now, imagine Earth during one of its mass extinction events. There have been several major ones, events that wiped out huge portions of life. The end Permian extinction, for example, is believed to have been the most severe, wiping out the majority of marine species. The end Cretaceous extinction is famous for wiping out non-avian dinosaurs. During these times, the surface world was chaotic. Temperature shifts, ocean acidification, changes in oxygen levels, collapses of food chains. If you're a shallow water species, you're exposed to all of it. If you're a deep water species, you might still be affected, but you may be less exposed to some of the most rapid surface disruptions. So deep habitats can act like refuges, and trenches, being even more isolated and stable, can be refugees within refugees. Now, the Mariana Trench is part of a subduction zone, where one tectonic plate slides beneath another. It is a geological feature that has existed in some form for millions of years, even though its exact shape and depth have changed over time. So the trench is not a temporary hole. It is a long-lived environment, and that matters because long-lived environments can host long-lived lineages. Now, how would a trench act as a refuge in practical terms? There are a few key mechanisms. First, depth itself creates separation. If a species lives deep, it is physically separated from many surface threats. Surface temperature changes might not reach it quickly. Surface predators might not reach it. Habitat destruction in shallow zones doesn't apply. Many human impacts, at least historically, didn't reach those depths. Second, deep environments can have stable temperature and chemistry compared to shallow environments. Even if the surface warms, deep waters can remain cold for long periods. That can protect cold-adapted species. Third, the deep sea can offer microhabitats in sediments, slopes, and ridges where organisms can persist even when other regions change. Fourth, trenches can trap organic material. They can collect sinking debris, which can provide food resources even when surface ecosystems fluctuate. So the trench can offer both stability and supply. Not abundant supply, but enough. Now, if you want to imagine prehistoric creatures surviving, this refuge idea is the most realistic framework, because it doesn't require a creature to be magical or impossible. It just requires it to have a deep habitat that remained viable while its shallow relatives disappeared. That is a pattern we already see in nature. There are species today that are relics of once more widespread lineages. They survive in specific refuges. They persist in isolated habitats. They become rare and localized. On land, you see this in animals and plants that survive in mountain valleys, isolated islands, deep caves, and remote forests. In the ocean, the deep sea can serve a similar role. Now, here's something important. A refuge does not guarantee comfort. A refuge can be harsh. It can be a place where life barely survives. But survival is enough. If a lineage can survive, it can continue. And the deep ocean is full of organisms that survive in low-energy conditions. That's why deep-sea animals often have slow metabolism, slow growth, and long lifespans. They are built to endure. Endurance is the deep ocean's theme. Now, when we talk about hiding from extinction, we also have to talk about isolation and evolution. If a population becomes isolated in the deep, it may diverge from its shallow relatives. Over time, it may become a distinct species. It may develop unique adaptations. It may become specialized to that deep habitat. So a refuge doesn't just preserve life, it can generate new life. The trench can act as both a shelter and a laboratory. Now, what kinds of animals are most likely to use the trench as a refuge? Not giant predators that need constant food. More likely, small to medium-sized organisms that can survive on scarce resources. Scavengers like amphipods. Deposit feeders like worms and sea cucumbers. Microbes that process sediment. Fish like snailfish that can adapt to pressure and feed on small prey. These are the kinds of organisms that can persist in a stable deep environment. And some of these lineages may have deep evolutionary roots. Now, this is where the prehistoric feeling comes in. If a lineage survives in a refuge for millions of years, it can retain traits that look ancient. It may not need to reinvent itself. It may keep a body plan that works. It may change slowly. So the trench can preserve a sense of ancientness, not because evolution stopped, but because the environment didn't force rapid redesign. Now, there's another reason the trench can feel like a refuge from extinction. Human activity. For most of human history, the deep ocean was beyond our reach. We could fish near the surface. We could sail above it. We could drop lines and nets to certain depths. But the trench was inaccessible. So the trench was, for a long time, a refuge from humans. No trawling, no habitat destruction, no direct hunting, no constant noise, no artificial light, no extraction. That has changed somewhat in the modern era with deep-sea exploration and with pollution reaching even the deepest points. But historically, the trench was one of the few places on Earth that humans did not directly disturb. That matters because humans are one of the most powerful drivers of extinction today. So the trench can feel like a refuge not just from ancient extinctions, but from modern ones. Now, this is not to say the trench is safe. We have found pollution there. Microplastics, chemical contaminants, human debris. The trench is connected to the surface, and sinking material can carry our waste down. So the trench is not untouched, but it is still less directly exploited than many shallow ecosystems. Now let's talk about another aspect of refuge. The deep sea is often described as a place where ancient animals live, but sometimes that's because the deep sea contains animals that look primitive to us. Soft bodies, reduced eyes, pale coloration, slow movement. These traits can make an animal look like it belongs to an earlier stage of evolution, even if it doesn't. So the trench can create prehistoric-looking animals simply through adaptation. A refuge can preserve ancient lineages, but it can also produce animals that look ancient because they are stripped down for efficiency. So the trench can feel prehistoric in two ways at once. It can preserve, and it can simplify. Now there's another layer. Trenches are not uniform. They have slopes, sediment plains, rocky areas, and different chemical conditions. They can host micro-habitats that support different communities, so even within a single trench, there can be pockets of diversity, and pockets of diversity are where unusual lineages can persist. If a certain slope has a slightly different sediment composition, it might support a different microbial community. That microbial community might support different invertebrates. Those invertebrates might support different predators. Small differences can cascade, so the trench can act like a patchwork of refuges. Now, if you're thinking, so the trench is a refuge for small creatures, but what about the dramatic ones? The answer is that even small creatures can be dramatic when you consider what they represent. A trench amphipod is not just a shrimp-like scavenger. It's a crustacean lineage that has adapted to crushing pressure. It's a survivor of an environment that would destroy most animals instantly. A trench snailfish is not just a soft fish. It's a vertebrate that solved the chemistry problem of high pressure. A trench worm is not just a worm. It's part of an ancient body plan that still works in one of the harshest habitats on Earth. So the trench doesn't need big creatures to feel prehistoric. It needs persistence. Now there's another reason refuges matter for our story. If the trench acts as a refuge, then it can also act as a source of recolonization. When surface environments recover after disruptions, deep refuges can provide survivors that expand back into shallower habitats. This is a concept in ecology and evolutionary biology. Refuges can preserve genetic diversity and lineages that later spread, so the deep ocean can influence the broader ocean's recovery and evolution. Now, this idea also connects to the feeling that the trench is a hidden reservoir of life. Not just a place where things hide, but a place where life can wait. Now, as we move forward, we're going to shift from the idea of refuge to the idea of signals. Because even if the trench hides life, it sometimes gives hints. Not through sightings, but through sound. The deep ocean is not silent. It's full of noises, geological, biological, mechanical. And sometimes we record sounds that we can't immediately explain. Strange calls, low-frequency rumbles, sharp pulses, noises that feel too large to come from something small. So next, we're going to talk about strange sounds in the abyss, what we've recorded, what might cause them, and why sound is one of the most haunting ways the deep ocean reminds us that it is still alive. If you've ever been in a room that was completely dark, you know what happens to your senses. Your eyes stop being useful, and your attention shifts. You start listening more carefully. You notice small noises you would normally ignore. A creak in the floor, the hum of an appliance, a distant car outside. In darkness, sound becomes the main way you understand what's around you. The deep ocean is like that, except it's darker than any room you've ever been in, and it's so large that around you can mean miles away. And the strange thing is, the deep ocean is not silent. It is full of sound. Some of it is natural, some of it is biological, some of it is geological, some of it is human-made, some of it is the ocean itself moving in ways we don't think about. And every so often, we record something that doesn't immediately fit into a neat category. A sound that is too loud, too low, too long, too patterned, too strange, something that makes even experienced researchers pause and say, "We don't know what that is yet." Those are the sounds that keep the deep ocean feeling alive and mysterious, even when we can't see anything. Because sound travels extremely well underwater, much better than light. Light gets absorbed quickly. Even in clear water, sunlight fades with depth, colours vanish, darkness takes over. Sound, on the other hand, can travel for long distances underwater, especially low-frequency sound. Water is a dense medium, and sound waves move through it efficiently. So in the deep ocean, sound is the long-distance language of the environment. It's how whales communicate across vast distances. It's how storms can be heard underwater. It's how earthquakes and volcanic activity announce themselves. It's how ice cracking can echo through water. It's also how humans leave their signature behind, through ships, sonar, drilling, and other activity. So when we talk about strange sounds in the abyss, we're talking about a deep soundscape that is always active, even when it feels like nothing is happening. Now, one of the most important things to understand about deep ocean sounds is that unexplained doesn't always mean mysterious creature. It often means we don't have enough context. Sound recordings can be tricky. A hydrophone picks up vibrations, but it doesn't show you what caused them. A sound can be distorted by water layers, temperature gradients, and reflections off the seafloor. A sound can travel far from its source, so you can record something strange and not know whether it happened nearby or hundreds of kilometers away. That uncertainty is what makes deep ocean sound so haunting. You hear it, You know something caused it, but you can't see it. Now, let's talk about the kinds of strange sounds that have been recorded in the deep ocean, because there are a few famous categories. One category is whale vocalizations. Whales produce some of the most powerful and complex sounds on Earth. Blue whales produce low-frequency calls that can travel long distances. Sperm whales produce clicks used for echolocation. Humpback whales produce songs that can be structured and evolving. Sometimes, whale calls sound strange simply because we aren't used to hearing them roar without context. A low moan can sound like machinery. A series of clicks can sound like a malfunctioning device. A call can sound alien because it's not meant for human ears. And sometimes, unusual recordings turn out to be whale sounds that were not previously documented or not previously recognised. Another category is ice. Ice can create sounds that are surprisingly eerie. When icebergs crack, shift, or break apart, they can produce long, resonant noises that travel through water. In some cases, ice-related sounds have been mistaken for biological sounds. Even though the Mariana Trench is not an icy environment, this category matters because it shows how powerful non-biological sounds can be underwater. The ocean can create noises that feel alive, even when they're just physics. Another category is earthquakes and geological activity. The Mariana Trench exists because of tectonic forces. It is part of a subduction zone where plates interact. That means the region is geologically active. Earthquakes can create deep rumbling sounds. Submarine landslides can create sudden crashes. Rock movement can create scraping or popping sounds. These sounds can be picked up by hydrophones, and they can sound like something massive moving in darkness, because in a way they are. It's the planet moving. Now there's also the category of human-made sounds. Ships produce noise. Propellers create low-frequency vibrations. Sonar produces pulses. Industrial activity creates a variety of sounds that can travel far. Sometimes, a strange sound is just a ship in the distance, distorted by water layers. Sometimes it's military sonar. Sometimes it's a research vessel. Sometimes it's equipment noise. And because the deep ocean is hard to monitor, it's not always obvious what human activity is happening nearby. So some unexplained sounds become explained later when someone matches the timing to ship movements or known sonar events. But not all sounds are so easily matched. Now, one of the most famous deep ocean mystery sounds is the bloop. The bloop was a powerful ultra-low frequency sound detected in 1997 by the US National Oceanic and Atmospheric Administration's hydrophone arrays. It was extremely loud, and it was detected across a large area. When people first heard about it, the imagination went wild. A giant creature, a deep-sea monster, something enormous calling from the abyss. It became a perfect modern ocean legend because it was sound-based. You could hear it, but you couldn't see it. Later, scientists suggested the sound was likely caused by ice-related events, such as ice quakes or the cracking and breaking of icebergs. That explanation makes sense, and it fits the idea that the ocean can produce huge sounds without requiring huge animals. But the bloop remains important in the public imagination because it shows how easy it is for sound to become a monster story. You hear something big, you assume something big made it. And sometimes that assumption is wrong, but sometimes it might not be. Because the deep ocean does contain large animals that produce sound. Whales are the obvious example, but other animals can produce noises too. Some fish can produce sounds, some crustaceans can snap. Even the movement of large animals through water can create low-frequency disturbances. Now, here's where it gets interesting. The Mariana Trench region is not known as a whale habitat, in the way some other regions are, but whales can travel across oceans. They can pass over deep areas, they can dive, they can produce sounds that travel far, so a hydrophone near the trench could pick up whale sounds from far away. It could also pick up geological sounds, it could pick up storms, it could pick up human activity. And because sound travels so far, the trench becomes part of a larger acoustic environment. So the strange sounds in the abyss are not necessarily coming from the trench bottom. They are part of the deep ocean soundscape around it. Now, another famous category of strange sound recordings involves what are sometimes called bioduck sounds, upsweep, and other named acoustic events. These are sounds recorded by hydrophones that were initially unexplained. Some have later been attributed to whales, such as Antarctic minke whales in the case of bioduck sounds. Others remain less clear or have multiple possible sources. The point is that the deep ocean has an acoustic catalogue of strange signals, and not all of them are fully mapped to known sources. That doesn't mean there are monsters, it means the ocean is complex and we have not fully listened to it. Now, let's talk about why sound is such a powerful trigger for the prehistoric feeling. When you hear something without seeing it, your brain goes into an older mode. On land, early humans would hear rustling in grass, a branch snapping, a distant roar. Sound often meant danger. It meant something moving nearby, something unseen. So sound without sight creates tension. In the deep ocean, we're always in that situation. We can't see far, we rely on instruments. We rely on sonar and hydrophones. So when we hear something strange, it feels like a presence. Something out there. And because the deep ocean already feels ancient, that presence feels prehistoric. Now, here's another reason deep ocean sounds can be hard to explain. The ocean has layers. Temperature and salinity create density gradients. These gradients affect how sound travels. Sound can bend. It can refract. It can travel through channels like the Siphonophore channel, which allows sound to travel long distances with less loss. So a sound recorded in one place may have originated far away, and it may have been shaped by the ocean structure. That makes it difficult to pinpoint sources, and that uncertainty creates room for speculation. Now, to connect this back to our topic, what prehistoric creatures still hide in the Mariana Trench? Strange sounds matter, because they represent one of the only ways we might detect something large without seeing it. If a large animal existed in deep water and produced sound, we might hear it before we ever filmed it. But there's a problem. Most deep-sea animals don't produce loud, long-distance sounds the way whales do. Many deep-sea creatures are quiet. They rely on stealth. They don't need to call across miles, so the likelihood of a trench monster announcing itself acoustically is low. However, the deep ocean could still produce sounds from large organisms indirectly. For example, a large animal moving through water can create turbulence. Feeding events can create noise. Groups of animals can create patterns. And if we don't have enough context, those noises can feel unexplained. Now, another interesting aspect of deep ocean sound is that sometimes the unexplained part isn't the sound itself, but the behaviour behind it. For example, a whale call might be recognised, but the location might be surprising. A pattern might change. A timing might not match known migration. That can suggest behaviour we don't understand. And in the deep ocean, behaviour is one of the biggest unknowns. We know some species exist, but we don't know what they do all the time. We don't know where they go. We don't know how they interact. So sound becomes a way to glimpse behaviour. Now imagine a deep ocean hydrophone recording an unusual pattern of clicks or pulses. It might be a whale. It might be a fish. It might be a geological event. It might be equipment noise. But until you match it to a source, it remains a mystery. And the deep ocean collects mysteries like that because we simply don't have enough sensors everywhere. We don't have enough listening posts. We don't have enough long-term monitoring. We have moments of listening, not constant awareness, so the abyss remains acoustically haunted. Now, there's another element here that people don't always think about. The ocean is getting louder. Human activity has increased noise pollution in many marine environments. Ships, sonar, industrial activity all contribute to the soundscape. This can affect animals that rely on sound. Whales can be disrupted, communication can be masked, stress can increase. So the deep ocean soundscape is not just a curiosity, it's an ecological issue. And in the trench, where life is already living on the edge of energy scarcity, added stressors can matter. Now, as we move forward, we're going to shift from what we hear to what we can't see. Because even if we had perfect hearing, the deep ocean would still hide most of its life from us simply by being difficult to explore. We have limited submersibles, limited time, limited coverage, limited ability to collect fragile organisms, and that means the trench remains in many ways a blank spot, not because nothing is there, but because we haven't looked enough. So next we're going to talk about what we still can't see, the limits of deep sea exploration, and why the Mariana Trench remains one of the most promising places on Earth for undiscovered life, even if that life isn't the giant monsters people imagine. The Mariana Trench is not mysterious because it's magical. It's mysterious because it's hard to reach, hard to stay in, hard to observe, hard to measure, hard to understand. If you've ever tried to find something small in a dark room with a flashlight that only shines a few feet ahead, you already understand the basic problem. You can search for a long time and still miss what's right in front of you, simply because your view is narrow and your time is limited. Now imagine that room is the size of an ocean. Imagine the flashlight has to survive crushing pressure. Imagine you can only use it for a few hours or a few days at a time. And imagine that every time you touch anything, you risk breaking it, disturbing it, or destroying the very thing you're trying to study. That is deep sea exploration. And the limits of deep sea exploration are the reason the trench still feels like a place where prehistoric creatures could hide, not because it's full of dinosaurs, but because it's full of blind spots. We have blind spots in our maps, blind spots in our cameras, blind spots in our sampling methods, blind spots in our understanding of behaviour, blind spots in our ability to bring organisms to the surface intact. So even though the trench has been visited, even though we have footage, even though we have collected samples, the truth is that we have still seen only a tiny fraction of what is there. Now let's start with the most basic limitation, depth. The Mariana Trench is nearly 11 kilometres deep at its deepest point. That number is easy to say, but it's hard to truly imagine. If you dropped Mount Everest into the trench, the peak would still be underwater. That's the scale, and depth creates multiple problems at once. Pressure increases with depth, which forces all equipment to be built like a pressure-resistant capsule. That adds weight, cost, and complexity. Temperature drops, which affects electronics, batteries, and mechanical systems. Darkness is total, which means you need artificial light to see, and artificial light changes animal behaviour. Communication is limited because radio waves don't travel well underwater, so you rely on acoustic communication, tethered cables, or autonomous systems. And time becomes expensive, because getting to the bottom takes hours, and every hour of operation is limited by battery life and system endurance. So the first limit is simply that the trench is far away, not in horizontal distance but in vertical distance. It's a long descent. Now the second major limitation is coverage. Even when we send a submersible down, it only sees a small area. The seafloor is vast. The trench system stretches for thousands of kilometres. The slopes and surrounding deep ocean add even more area. A camera on a submersible might capture a narrow field of view, a small patch of seafloor, a limited range in front of it. That means we don't explore the trench the way we explore a forest. We don't walk through it for months. We don't set up dozens of cameras everywhere. We don't observe every animal we encounter. We visit tiny points. We sample tiny patches. We come back with a handful of data. And then we try to build a picture of an enormous environment from that. It's like trying to understand an entire continent by looking at a few square meters. Now there's also the problem of time. Deep sea expeditions are short compared to the timescales of deep sea life. A submersible might spend a few hours on the bottom. A lander might sit for a day or two, sometimes longer but still limited. But deep sea animals might have slow behaviours. They might not respond quickly. They might move slowly. They might be active only at certain times. They might avoid disturbance. So it's possible to visit an area and see almost nothing, even if life is present, because you didn't stay long enough. This is one reason baited cameras are so commonly used. Bait is a shortcut. It draws scavengers in. It guarantees activity. But bait creates a bias. You mostly see scavengers. You mostly see animals attracted to food. You mostly see creatures that respond to scent. That means our footage can overrepresent certain groups, like amphipods, and underrepresent others, like animals that don't care about bait or actively avoid it. So our view of trench life is shaped by our methods. We see what our tools allow us to see. Now let's talk about another limitation: fragility. Many deep-sea organisms are fragile, especially gelatinous animals. Even some fish and invertebrates can be delicate. When you try to collect them with nets, suction samplers, or traps, they can be damaged, even if you manage to collect them. Bringing them to the surface changes pressure. Decompression can destroy tissues. Temperature changes can stress the organism. The animal might die or deform before you can study it properly. This means some deep-sea organisms are effectively invisible to traditional sampling. They exist, but they don't survive collection. So our knowledge is biased toward animals that can be caught and brought up. Hard-bodied animals, robust crustaceans, certain fish. But the deep sea also contains soft-bodied organisms that may be undercounted. Now there's also the issue of scale. Some deep-sea animals are small, very small. Tiny crustaceans, microbes, larval forms, worms, protists. These organisms can be abundant, but they are easy to miss unless you take sediment samples and analyse them carefully. So the trench can contain entire communities that are invisible to a camera. A camera might show an empty seafloor, but the sediment could be full of life. Now another limitation is identification. Even when we collect organisms, identifying them can be difficult. Some deep-sea species look similar to each other. Some are new to science, some have subtle differences. Some require genetic analysis to confirm, so it's possible that we've already collected unknown species and not fully recognised them yet, or that we have recognised them as new, but haven't fully described their biology. Deep-sea taxonomy is a slow process, and that means the deep ocean can contain undiscovered diversity simply because we haven't had time to process it all. Now, let's talk about the limitation of technology. We have made huge progress in deep-sea exploration, but our tools still have limits. Manned submersibles can go deep, but they are rare, expensive, and risky. They require extensive support. They can only operate for limited periods. Remotely operated vehicles, ROVs, are powerful, but they are usually tethered to a ship. That tether limits range and manoeuvrability. The ship must remain above, which is expensive and weather-dependent. Autonomous underwater vehicles, AUVs, can travel without a tether, but they have limited battery life and limited ability to react to unexpected discoveries. They can map and survey, but detailed observation is still challenging. Deep-sea landers can sit on the bottom and record, but they are stationary. They only show what comes to them. So every tool has trade-offs, and none of them give us the kind of constant, wide-area, high-resolution observation that would make the trench feel fully known. Now consider another limitation: light. To film in the deep, you need artificial light. But artificial light changes the environment. It can attract animals. It can scare animals. It can alter behaviour. Some deep-sea animals are sensitive to light because they live in darkness. A bright light can be overwhelming. It can cause avoidance. So a submersible might arrive, turn on its lights, and the animals might leave. Or they might freeze. Or they might behave in unnatural ways. So the act of observing can distort what you observe. This is why researchers sometimes use red light or low light cameras, trying to reduce disturbance. But there are limits. You still need some light, unless you rely on natural bioluminescence, which is difficult to film, so light is both necessary and disruptive. Now, there's also the limitation of sound and vibration. Submersibles and ROVs make noise. Thrusters create vibrations. Mechanical systems hum. Even small noises can travel far underwater. Deep-sea animals may detect those vibrations, They may respond by hiding or fleeing. So again, observation is intrusive. It's like trying to watch wildlife while driving a loud truck through the forest. You will see some animals, but you will miss others. Now, another limit is the environment itself. The trench floor is not smooth and open everywhere. It can have steep slopes, unstable sediments, and rugged terrain. Landslides can occur. Sediment can be soft and thick. A submersible can sink or stir up clouds of sediment that reduce visibility. So even when you reach the bottom, you may not be able to see well. The seafloor can become a brown fog. That makes filming difficult. It also means animals that live in sediment can remain hidden. Now, there's another subtle limitation that matters a lot. Behaviour. Even if we had perfect cameras, we would still struggle to understand deep-sea life, because behaviour is hard to capture. Many deep-sea animals might spend most of their time resting. They might feed rarely. They might reproduce in ways we haven't seen. They might migrate vertically. They might have seasonal patterns. So the deep ocean can contain behaviours that we have never observed simply because we haven't watched long enough. This is why long-term deep-sea observatories are so valuable. They can record over months or years. They can capture rare events. But building observatories in the trench is extremely challenging. So most of what we know is still based on short visits. Now, there's also the limitation of human expectation. We tend to look for things we recognise. We look for fish. We look for large animals. We look for movement. But the deep ocean may contain life that doesn't fit those expectations. Microbial mats, tiny organisms, slow-moving deposit feeders, transparent drifting predators, life that blends into sediment. So we might miss what we're not trained to notice. And that means the trench can hide life, not just because it's hard to reach, but because it doesn't announce itself in a way that fits our instincts. Now this is the core truth. The Mariana Trench is not a place we have explored. It's a place we have visited. We have reached it. We have filmed it. We have sampled it. But we have not mapped it biologically in a complete way. And until we do, the trench will remain a place where unknowns are not just possible but expected. Now the question is, what kinds of unknowns? Not necessarily giant prehistoric predators, more likely undiscovered species of small to medium-sized organisms, new amphipods, new worms, new microbial lineages, new snailfish species, new gelatinous organisms, new deep-sea crustaceans, and possibly new behaviours of known animals. Because sometimes the biggest discoveries are not new species but new ways of living. Now we're close to the end of our journey, but not in a wrap-it-up way. More in a step back and look at what this means way. Because if the trench remains difficult to explore, then it remains a place where mystery is natural. And that mystery is exactly what keeps the prehistoric feeling alive. So next we're going to move into the closing, where we bring all of this together, not as a final answer, but as a reminder that the deepest parts of our planet are still holding secrets, and that some of those secrets might not be monsters at all, but simply life that has been waiting quietly for us to finally notice it. When you think about the Mariana Trench for long enough, something strange happens. At first, it feels like a place you can summarise with a single idea. The deepest place on Earth. A dark pit. A crushing world where nothing should live. But the more you sit with it, the less it feels like a single idea. It starts to feel like a whole planet inside our planet. A place with its own rules. A place where pressure is not just a number, but a force that shapes bodies and behaviours. A place where food is not a given, but a rare gift that arrives as drifting fragments from above. A place where life survives not by being loud, but by being efficient. And when you look at it that way, the trench stops being a horror story and becomes something else. A reminder. That Earth still has places we don't truly know. That our maps are not the same thing as understanding. That even in the modern world there are habitats so extreme and so hard to reach that they remain, in a very real sense, hidden. And that's why the deep is still keeping its secrets. Not because it's trying to, because it can. We started with a question that sounds like a myth on purpose. What prehistoric creatures still hide in the Mariana Trench? And if you came into this expecting a single dramatic answer, something with a name and a silhouette and a set of teeth you could picture clearly, the trench doesn't really work that way. The trench doesn't hand you one monster. It hands you a system. It gives you amphipods that swarm a rare meal like a quiet storm. It gives you worms and deposit feeders that turn sediment into survival. It gives you snailfish that solve a chemistry problem most vertebrates can't. It gives you gelatinous life that drifts through darkness and disappears without leaving a trace. It gives you predators like dragonfish that hunt with invisible teeth and private light. It gives you sharks that carry an ancient blueprint, still effective after hundreds of millions of years. It gives you cephalopods that remind you the ocean has always been good at hiding large, intelligent, soft-bodied hunters. It gives you strange sounds that echo through water and make you wonder what moved, what cracked, what called out in a place you can't see. And it gives you a hard truth that is somehow more unsettling than any monster story. We have not looked enough. We have not listened enough. We have not stayed long enough. So the question isn't just what is hiding down there, it's also what have we been missing? Because the Mariana Trench is not empty. It's not dead. It's not a void. It's a living environment shaped by pressure, darkness, cold, and time. And life has had millions of years to learn how to survive there. That's the prehistoric feeling people sense when they think about the trench. Not that dinosaurs are swimming around under the seafloor, but that the trench contains strategies that feel ancient, survival strategies that don't rely on sunlight, predator designs that don't need speed, body plans that don't need change, a world where patience is as important as strength, a world where the most successful creatures are the ones that waste nothing. Now, if you're listening to this late at night or in a quiet moment, you might be picturing the trench as a place that is far away from you, a distant point on the map, a place you will never visit. But the truth is, it's part of your world. It's part of the same ocean that touches coastlines, shapes weather, moves heat around the planet, and supports life on a scale we still struggle to understand. The trench is not separate. It's connected. And that connection is why it matters. Because what happens in the deep ocean doesn't stay in the deep ocean forever. Energy moves, nutrients cycle, water circulates, life spreads, and even our pollution reaches down there, which is one of the most sobering reminders that the trench is not protected by distance alone. So when we talk about secrets, we're not talking about a fantasy world. We're talking about a real environment that is still largely unobserved. And that means the secrets are not just about creatures. They're about relationships, food webs we don't fully understand, behaviours we haven't seen, species we haven't named, adaptations we haven't studied. And the deeper you go, the more the unknown becomes normal. Now it's tempting to end this kind of story with a neat conclusion, to say, so here's the answer, and wrap it up like a solved mystery. But the trench doesn't give us that. The trench gives us a reminder that some mysteries remain open simply because we haven't earned the answer yet. We haven't spent enough time there, we haven't built enough tools, we haven't listened long enough, we haven't watched the deep in the way we watch the surface. So the deep keeps its secrets, not out of spite but out of scale, out of difficulty, out of distance, out of darkness. And that's why the Mariana Trench still feels like the last frontier. Because it is. Not the only frontier, but one of the most honest ones. A place where our technology still struggles. A place where our imagination still runs ahead of our data. A place where the line between unknown and undiscovered is still very thin. So if you find yourself wondering, even now, what else might be down there? What else might be drifting through the water column? What else might be crawling through sediment? What else might be passing just outside the reach of a camera's light? You're not being silly. You're doing what humans have always done when faced with a vast dark space. You're noticing that you don't have the full picture, and you're letting curiosity fill the gap. That curiosity is part of what makes the trench feel alive, not just because of the creatures, but because of the questions. Because every time we send something down there, we learn something new, and the new thing usually leads to another question instead of a final answer. That's how real exploration works. Now, before you go, I want you to hold on to one simple thought. The Mariana Trench is not a place where life should be, and yet life is there anyway. Not just surviving, but adapting, finding ways, persisting, quietly proving that Earth is more flexible than we give it credit for. So the next time you hear someone talk about deep-sea monsters, you don't have to argue with them. You don't have to laugh. You don't have to insist the ocean is fully known. You can just remember that the deep ocean has already surprised us before. It has already hidden giant squid in plain sight for centuries. It has already produced animals with transparent teeth and glowing bodies. It has already kept ancient lineages alive through changes that reshaped the surface world. And it will probably surprise us again, because the deep is still keeping its secrets. And for now, it seems perfectly content to let us wonder. So wherever you're listening from tonight, whether you're lying in bed, sitting in a quiet room, or letting this play in the background while the world slows down around you, I hope this made the ocean feel a little bigger. Not in a scary way, in a real way. In the kind of way that reminds you there are still places on Earth that don't belong to us. Places that don't care if we understand them. Places that exist on their own terms. And if you enjoyed this kind of calm journey into the unseen parts of the world, you already know what to do. You can leave a like, subscribe, and join us again here at Life Beyond Seen. Because there's always another mystery waiting, somewhere below the surface.